Hello there and welcome to Physics with William, where curiosity slows its breathing and big ideas are allowed to unfold at a more human pace. Tonight we're settling in with a question that sounds simple when you first hear it, but becomes stranger the longer you sit with it. Why can space and time not exist without each other? It is the sort of question that hides in plain sight. We move through rooms and roads and doorways without worrying too much about what space is. We wake, work, wait, eat, and sleep without often asking what time is. They seem familiar enough, almost too familiar, like air or gravity, or the reason toast always seems to land with a level of confidence it absolutely has not earned. Before we ease into it, I would love to know where in the world you're listening from tonight, and what time it is in your little corner of things right now. It feels fitting somehow. A quiet talk about space and time, while each of us arrives from a different place at a different hour, joined by a single stream of thought that crosses distance without much fuss. And if you find this soothing, or interesting, or just the right sort of company for the end of a long day, do consider liking the video and subscribing. It helps this calm little corner reach other people who might enjoy a slower way of exploring the universe. Now get comfortable. Let the day loosen its grip a little, and let us begin with an idea that has misled people for a very long time, partly because it feels so sensible. Most of us grow up thinking of space and time as two separate things. Space is where stuff is, time is when stuff happens. That division feels neat and practical. A chair is in the kitchen, breakfast happened an hour ago, the moon is in the sky, your alarm will go off tomorrow morning, which is either a useful fact or a deeply upsetting one depending on how early it is. In daily life, this separation works well enough. We can plan a train journey, meet a friend, bake a cake, or miss a dentist appointment with perfectly ordinary confidence using this simple picture. Space gives us position. Time gives us sequence. The world seems happy to cooperate. But physics has a habit of taking ideas that seem solid in ordinary life and asking whether they still hold up under closer inspection. And once people began asking the right questions and making very careful measurements, the neat separation between space and time began to look less like a deep truth and more like a convenient shortcut. It turns out that space alone does not tell the full story of where something is. Time alone does not tell the full story of when something happens. The two are tangled together much more tightly than common sense would like. To see why, it helps to begin with something familiar. Imagine a friend asks where you are. You say you're at a train station. That sounds like a complete answer, but it really is not. If they arrive tomorrow, you may no longer be there. If they arrived yesterday, they would not find you either. Your position in space only makes sense when paired with a moment in time. Where you are cannot be fully separated from when you are there. In ordinary life, we often leave that second part unstated because it is assumed. If you say you're in the kitchen, people understand that you mean now, or at least sometime close to now. But that assumption is doing a lot of work. The reverse is true as well. Suppose someone asks when the concert begins and you answer 8 o'clock. Again, that is not really complete. 8 o'clock where? If you're in Amsterdam and your friend is in New York, the same number on the clock refers to different moments in the wider world depending on location. Time, just like space, starts getting slippery the moment you try to treat it as universal and independent. We manage this in daily life by attaching time zones, calendars, schedules, and shared conventions. In other words, we quietly glue time to place in order to make sense of it. That alone is already interesting. Even before we reach modern physics, ordinary experience is giving us a hint. Space without time is incomplete. Time without space is incomplete. We can pretend they are separate because human life moves at modest speeds, on a modest planet under modest gravity. Our world is forgiving enough to let the illusion survive. But the deeper structure is there all along. For centuries, many thinkers believed the universe came with a sort of invisible grid for space, and a universal clock for time. Space was the giant stage. Time was the steady ticking in the background. Objects moved around inside space while time flowed on by itself, the same for everyone everywhere. It was a very successful picture for a long time. It helped explain falling apples, swinging pendulums, cannonballs, planets, and a great many other things besides. It felt orderly, sensible, clean. If the universe were a well-run theatre, space was the floorboards and scenery, while time was the stage manager calling cues from somewhere off stage. There is a reason that picture lasted. It works beautifully for the kinds of speeds and distances human beings first learned to measure. If you watch a cart roll down a road or a ship cross a harbour, you do not notice anything odd happening to time. If two people compare clocks after an ordinary day, nothing seems amiss. If you measure the length of a table, it does not appear to depend on who is walking past it. Everyday life reassures us again and again that the world is simple in this way. Space here, time there, separate shelves, neatly labelled. The trouble began when physicists started looking at light. Light refused to behave like ordinary things. If one car moves toward another, the relative speed changes in the way you would expect. But light did something far stranger. No matter how people moved, no matter how they chased it or measured it, the speed of light came out the same. That sounds technical at first, but its consequences are deeply unsettling. If the speed of light is fixed for everyone, then space and time cannot stay independent. One or both must adjust in order to preserve that result, and as it turns out, both adjust. This is where the universe stops nodding politely at common sense and starts rearranging the furniture. To understand the basic problem, imagine two people trying to describe the same event. One is standing still on a platform, another is moving very quickly on a train. In the old view, they might disagree about some details, but they should still share the same time flowing underneath everything. In the newer view, that shared time no longer survives. Their measurements of distance and duration depend on how they are moving. What one person calls a length, another person measures differently. What one person calls a span of time, another person does not fully agree with. Neither is mistaken. The structure of reality itself allows these differences because space and time flex together. That last part matters. They do not change randomly, they compensate for each other. If motion affects how distance is measured, it also affects how duration is measured. If one observer sees less space between 2 points, another effect appears in time as well. The universe is not making separate corrections to two unrelated things. It is treating them as parts of a single system. That is why physicists no longer think of space and time as independent ingredients. They are more like two aspects of one fabric. Now, fabric can be a slightly dangerous analogy because it can sound softer and more decorative than the concept deserves, as though the cosmos is a set of curtains chosen by a very ambitious interior designer. Still, it is useful if handled carefully. What matters is the idea of connectedness. Tug one part and another part responds. You do not have a separate cloth for length and a separate cloth for duration stitched together at the edges. You have one structure in which both are built in. That structure is what we call space-time, not space and time sitting next to each other like polite neighbours sharing a fence. Space-time. One word because, in the physics that best describes the universe, they are inseparable. An event is not just somewhere. It is somewhere and somewhen. A moving object is not simply changing position in space as time flows independently past it. It is tracing out a path through space-time. Everything you have ever done, every walk to the kitchen, every glance at the clock, every lost sock, every successful cup of tea and every regrettable cup of tea, has been a journey not merely through space over time, but through space-time as a unified setting. This can feel abstract until we pull it back toward life. Consider how we give directions. We rarely give pure spatial directions without a time component lurking in the background. Meet me at the cafe at 7. The package arrived yesterday at the office. The bus stops here in 10 minutes. Even the simplest acts of coordination require both location and timing. Try removing one and the other becomes almost useless. Tell someone only where to meet you, with no indication of when, and you may spend your afternoon wondering whether you have been abandoned. Tell them only when, with no indication of where, and the result is not much better. Human life itself is built around this partnership. The same applies in science, only with greater precision and much stranger consequences. A planet orbiting a star is not merely occupying different places one after another, while some outside clock keeps score. Its motion is part of the geometry of space-time. A beam of light travelling from a distant galaxy is not simply crossing empty space during a separate passage of time. Its path and the time associated with that journey are bound up together. Near a massive object such as a star or black hole, space does not just curve while time keeps minding its own business nearby. Time is affected too. In stronger gravity, clocks run differently. That is not a side note. It is the whole point. If gravity changes the structure you're moving through, then both the spatial and temporal parts of that structure respond. This is one of the reasons the old idea of gravity as a simple pulling force turns out to be incomplete. A better picture is that mass changes the geometry of space-time. Things then move according to that geometry. Once again, the key is union. If space could exist on its own as a separate arena, perhaps gravity would merely bend trajectories inside it. But that is not what happens. Time changes as well. If time could exist on its own as a separate flow, perhaps gravity would leave it untouched. But it does not. Put a clock higher up and a clock lower down in a gravitational field, and over time they no longer agree. Space and time answer together. And this is where the title of tonight's subject becomes more than a dramatic phrase. Why can space and time not exist without each other? Because the universe does not seem to offer them to us separately. The more accurately we describe reality, the less meaningful the separation becomes. There is no complete account of physical existence that uses only space while ignoring time, and no complete account that uses only time while ignoring space. A place is not fully real in physics unless it is tied to a moment. A moment is not fully real unless it is tied to a place. Remove one, and the other loses definition. It is a bit like asking for a melody without duration, or a road trip without distance. You can say the words, but the thing itself falls apart. Music needs time in order to unfold. Travel needs space in order to occur. And the physical universe, as far as we can tell, needs space-time in order for events to have any structure at all. There is also a deeper reason this inseparability matters. It changes what we mean by reality itself. In the older picture, the present moment feels universal. Now is now for everyone. Somewhere, a cosmic master clock keeps the official version. But once space and time are joined, that clean universal present begins to dissolve. Different observers moving relative to one another do not always agree on what counts as happening at the same time. That's a disturbing idea when you first meet it. It suggests that the slice of reality you casually call now is not a single shared sheet laid across the universe. It depends on motion, perspective, and the structure of space-time. The world becomes less like a room lit all at once and more like a vast arrangement in which timing itself depends on how you travel through it. At first, that can feel like the universe has become less solid. In truth, it has become more precise. The comforting old picture was simple, but simplicity and truth are not always best friends. Sometimes they are more like polite colleagues who avoid discussing important matters. The union of space and time gives us a stranger universe, but also a more accurate one. It explains why light behaves as it does, why moving clocks differ from resting ones, why gravity alters duration, why the cosmos can expand, and why events are best understood not as dots in a room with a clock on the wall, but as locations in a four-dimensional structure. If that sounds grand, it is because it is. But it is also quietly intimate. Your life is not happening inside space while time pours over it like rain. Your life is a path through space-time. The place where you were born and the hour you were born are not separate facts that only happen to share a birth certificate. Together they identify an event. The same is true of every step you have taken since. every laugh, every delay, every train missed by an amount so small that you still believe it should count as making it. All of it belongs to this combined framework, and yet, for all that, we do not feel space-time directly. We feel rooms, distances, clocks, boredom, deadlines, waiting, aging. We feel the human version of things. Physics then comes along and says that underneath those ordinary experiences lies a deeper unity that daily life only hints at. It is not asking you to abandon common sense entirely. It is asking you to notice that common sense was built for a small corner of reality. Fast motion, intense gravity, cosmic distances, and precise measurement reveal a different order beneath the familiar one. So tonight we begin there, with the old separation starting to loosen. Space is no longer merely where. Time is no longer merely when. They answer to one another. They keep each other meaningful. And before we can understand how that union was uncovered, or why light forced physicists to rethink the stage and the clock, we need to spend a little more time with the older picture first, because it is only by seeing how natural it once seemed that we can appreciate how remarkable it was when the universe quietly refused to keep space in one box and time in another. For a very long time, the most sensible way to think about the universe was also the simplest. Space was where things happened, and time was what kept them in order. One gave you position, the other gave you sequence. If you wanted to describe the world, you could point to a place and glance at a clock, and between the two of them you had what seemed like a complete picture. It was tidy, dependable, and reassuring in the way old furniture is reassuring. Perhaps a little worn around the edges, but still sturdy enough to trust. This older view did not arise because people were foolish. Quite the opposite. It arose because it matched experience so well that it would have been strange not to believe it. If you stand in a field and watch a cart move from one gate to another, the cart changes position in space while time passes in the background. If you toss an apple upward, it rises and falls while the seconds tick on by. If you look at the moon on 2 different nights, it has changed place in the sky and a day has gone by. Space and time appear side by side, cooperative but distinct, like 2 clerks in a quiet office, each handling their own pile of papers. Ancient thinkers approached the question in different ways, but many shared the sense that place and change were deeply important. Aristotle, for instance, thought carefully about motion, place and duration, though not in the modern scientific sense. He imagined a cosmos where objects had natural tendencies, where heavy things sought the centre, and where the heavens moved with a different kind of perfection than earthly matter. His world was ordered, layered, and purposeful. Time, in that picture, was tied to change, especially the regular changes of the heavens. The turning of the skies offered a kind of cosmic rhythm. You did not need a wristwatch when the universe itself was putting on a daily performance overhead. That already tells us something useful. Long before precision clocks and laboratory measurements, human beings linked time to repeating motions. The rising of the sun, the phases of the moon, the return of the seasons. These were not just markers of life, but the earliest dependable signatures of time itself. If the river flooded, if the stars shifted, if winter followed autumn as it always did, then the world had a cadence. Time was not an object you could hold, but it could be counted through regular change. Space, meanwhile, was where these changes occurred. The field, the temple, the harbour, the hillside. One was the setting, the other was the order in which events arrived. As civilizations became more organised, this practical separation became even more useful. Farmers needed calendars, priests needed ritual timing, merchants needed schedules, sailors needed position, builders needed geometry. None of this required anyone to believe space and time were fundamentally woven together. In fact, it was far easier to treat them separately. If you're trying to know when to plant crops, time matters. If you're trying to know where the boundary stone sits, space matters. If you're trying to know when and where to collect taxes, both matter, though one suspects the taxpayers were not especially comforted by the distinction. and then as natural philosophy slowly evolved into something more mathematical. The old picture became sharper and more formal. By the time of Galileo, people were beginning to describe motion with a new kind of discipline. Objects could be tracked, distances measured, intervals timed, and patterns extracted. This was a major shift. The world was no longer merely being described through broad philosophical categories or common observation. It was being measured. Motion became something you could analyze rather than simply notice. Galileo helped prepare the way by studying how objects fall and how motion behaves when stripped of old assumptions. He challenged the idea that heavier objects must fall faster simply because it felt natural. He paid attention to what actually happened rather than what tradition expected to happen. He also grasped something important about relative motion. If you're inside a smoothly moving ship and everything with you is moving along steadily, many ordinary motions look the same as they would on land. A dropped object falls straight down. A tossed ball behaves normally. This was an important clue about how motion depends on the observer, though it did not yet shatter the old separation of space and time. It merely loosened the hinges a little. Then came Isaac Newton, and with him the old picture reached its most powerful and elegant form. If earlier thinkers had furnished the room, Newton walked in, arranged the shelves, labelled the drawers, and somehow made the whole place feel inevitable. In Newton's universe, space and time were not just convenient categories. They were the stable framework in which everything physical took place. Space was absolute. Time was absolute. Objects moved through space as time flowed steadily onward, unaffected by the objects within it. The cosmos became a grand mechanical system, vast and orderly, governed by precise laws. This was an extraordinary achievement. Newton did not merely offer a story about apples falling or planets circling. He created a unified framework that could describe both. The same laws that governed a stone tossed from a tower could also govern the moon in orbit. This was the sort of intellectual moment that changes everything afterward. Once you can describe the heavens and the earth with the same basic rules, the universe starts to look less like a collection of separate realms and more like one coherent machine. In that machine, space was the stage. Not a metaphorical stage in the gentle literary sense, but a real and fixed arena. It existed whether anything occupied it or not. Empty space was still space. It had extension, direction, and structure. You could imagine removing every planet, every star, every crumb of dust, and space would still remain, vast and ready, like an empty theatre waiting for actors to arrive. Time was the clock. It flowed uniformly, independently, without needing events in order to exist. Remove all motion, silence every process, stop every heart, and time would still continue. It was not dependent on change. It was the background against which change could be measured. Newton himself described absolute time as flowing evenly without regard to anything external. That is a remarkable idea when you sit with it for a while. It means time is not just what clocks happen to measure. It is something deeper, something the clocks are trying to track. A real universal stream, moving the same way for everyone, everywhere. If two events happen far apart, there is still a fact of the matter about which came first, how long separated them, and what the universe's invisible master clock would say about it all. Time, in this picture, does not wobble, stretch, or negotiate. It simply proceeds. This view fit ordinary experience so well that it was almost irresistible. After all, when two people compare watches after a normal afternoon, they do not find dramatic disagreements. A road stays the same length whether you stroll down it or sprint. A minute feels like a minute whether you're in the kitchen or the garden, though admittedly it may feel considerably longer if you're waiting for unpleasant news or assembling flat-pack furniture. For the scales of daily life, Newton's world worked magnificently. It also gave science a deep sense of confidence. If space and time are fixed and universal, then nature becomes legible in a particularly comforting way. there is one real geometry of the world and one true timeline of events. If measurements disagree, it must be because someone observed poorly, or a device was faulty, or a calculation went astray. The universe itself is not ambiguous. It has one correct arrangement. For scientists, this is wonderfully convenient. It means the cosmos may be difficult, but it is not slippery. The image of space as a stage is especially helpful here, because it captures the passivity Newton assigned to it. The stage does not care whether a tragedy or comedy unfolds upon it. It does not change when a character exits or enters. It simply remains, allowing the action to take place. In the same way, Newtonian space does not care whether planets orbit, cannons fire, or rain falls on Tuesdays. It stays fixed. Directions remain directions. Distances remain distances. The actors may rush about with all manner of drama, but the stage floor keeps its composure, and time as a clock completes the picture. The clock does not take sides. It does not hurry for the king or slow for the peasant. It ticks on with perfect indifference. That was the great beauty of absolute time. It was impartial. A pendulum could be trusted because it was measuring a reality already there. A more accurate clock did not create better time. It merely revealed more faithfully the steady flow that existed anyway. There was, however, a quiet philosophical tension inside this elegant picture. Not everyone agreed that space and time should be treated as independent things. Gottfried Wilhelm Leibniz, one of Newton's great intellectual rivals, argued for a different view. He did not think space was an empty container existing on its own. Instead, he saw space as a system of relations among objects. Likewise, time was not a river flowing independently in the background, but an ordering of events. Without objects and events, talk of space and time seemed to him empty. If there were no things, what would positions even mean? If nothing happened, what would time be measuring? This disagreement is more than a historical footnote. It goes straight to the heart of the issue. Newton's view says the stage exists even if the theatre is empty. Leibniz's view says an empty stage with no actors, no scenery, no audience, and no events is not really a stage in any meaningful sense. Newton says the clock keeps ticking even if the universe falls silent. Leibniz asks what ticking could possibly mean if there is nothing to mark, compare, or change. At the time, Newton's framework proved far more successful in practical physics. It generated predictions, explained motion, and supported a huge expansion of scientific understanding. When one view helps you calculate planetary orbits and the other is busy asking awkward philosophical questions, history tends to reward the calculator first. Still, the awkward questions do not always stay quiet forever. For generations, though, the Newtonian picture reigned with remarkable success. Engineers built machines with it. Astronomers mapped the skies with it. Navigators crossed oceans with it. Architects, artillery officers, clockmakers, and mathematicians all benefited from its clarity. It became woven into educated common sense. Even people who never read a line of Newton absorbed the worldview indirectly. Space was the area something occupied. Time was the sequence through which it moved. Reality felt orderly because the invisible framework beneath it was assumed to be stable. There is something deeply satisfying about that sort of universe. It behaves. It keeps appointments. It may be vast and difficult, but it is never fundamentally mischievous. If something goes wrong, it is your fault, not the cosmos changing the rules because you moved too quickly or wandered too close to a massive object. A table is a table, a second is a second. A field stretches in all directions with calm indifference. It is the kind of universe in which one imagines a good telescope, a clean notebook, and a decent cup of tea might eventually explain almost everything. Yet even in such a tidy world, some peculiar questions began to appear once people took light and electromagnetism seriously. At first, these did not look like a threat to the basic structure of space and time. They looked more like technical difficulties, The sort of thing clever people in waistcoats would surely sort out with more measurements and stern expressions. Light, after all, was just another physical phenomenon, was it not? Surely it must fit into the same framework as everything else. But light turned out to be a rather uncooperative guest. Before the trouble became obvious, physicists often imagined that light waves, like sound waves, must travel through some medium. Sound travels through air, water waves travel through water, and so light, it seemed reasonable to suppose, must travel through an invisible medium filling space. This hypothetical substance was called the ether. It was thought to be everywhere, even in the emptiness between planets and stars. The ether would give light something to move through, preserving the intuitive idea that waves require a supporting background. This was still very much in the old spirit. Space remained the stage, but now perhaps it came furnished with an invisible substance. Time remained universal. Nothing too dramatic yet. If Earth moved through this ether, then careful experiments ought to detect our motion relative to it. One might expect light to behave slightly differently depending on the direction in which Earth was moving, just as the sound of wind or water feels different depending on how you travel through it. That expectation set the stage for one of the great surprises in physics. Experiments designed to detect motion through the ether failed. Not failed in a small, mildly disappointing way, but failed stubbornly. The most famous of these, carried out by Albert Michelson and Edward Morley, found no clear sign that Earth was moving through such a medium at all. Light speed appeared unchanged in a way that did not sit comfortably with the old framework. Now, this did not instantly overthrow the Newtonian world. Scientific revolutions are rarely so theatrical. People tried to patch the picture. Maybe the ether dragged along with Earth. Maybe measuring devices changed in subtle ways. Maybe there were effects not yet understood, and to be fair, patching a successful theory is often sensible. You do not demolish the house because one window sticks. You oil the hinges and see what happens. But the difficulty kept growing. Electromagnetism, especially through the work of James Clerk Maxwell, had already described light in a way that implied a definite speed. And if that speed was to remain fixed, regardless of the observer's motion, then the old separate absolutes of space and time were in danger. Something would have to give. This is where the old image of space as stage and time as clock begins to show strain. A fixed stage is easy to imagine when actors move around slowly and predictably. A universal clock is easy to imagine when all observers can agree on how events line up. But if nature insists that light behaves the same for everyone, then the stage cannot remain entirely rigid and the clock cannot remain entirely universal. Distances and durations begin to look less like independent certainties and more like measurements tied to the observer's state of motion. That conclusion was not yet fully drawn, but the pressure was mounting. It is a bit like hearing a faint creak in the beams of a house you have trusted all your life. At first, you ignore it. Then you hear it again on a windy night. Then one day the floor shifts just slightly beneath your feet, and you realize the building may be sturdier than you knew in some ways, but less simple in others. The remarkable thing is that none of this made Newton foolish or obsolete in the ordinary sense. His framework still worked, and still works, for a huge range of everyday situations. Bridges do not collapse because relativity exists. Tennis balls do not suddenly require exotic geometry. The old stage and clock remain excellent approximations for much of life. That is part of what makes the history so interesting. The universe did not humiliate the older picture so much as reveal its limits. It said, in effect, yes, this is a very good sketch, but not the final portrait. And that is often how science advances, not by declaring everything before it nonsense, but by showing that a trusted idea is part of a larger and stranger truth. Space as a stage and time as a clock was one of the greatest ideas ever built. It organized centuries of thought. It allowed people to predict eclipses, engineer machines, and imagine the cosmos with new confidence. It turned motion into mathematics, and the heavens into something understandable. If it eventually proved incomplete, that only makes its success more impressive, not less. Still, once the cracks begin to show, curiosity has a way of leaning closer. If light will not cooperate with the old arrangement, then perhaps the arrangement itself must be reconsidered. If observers in motion cannot agree on the same neat background picture, then perhaps the stage is not rigid after all. Perhaps the clock is not universal. Perhaps what seemed separate was never truly separate to begin with. That shift did not happen all at once. It required someone willing to look at the problem without clinging to the furniture of common sense. Someone willing to ask what must be true if light's strange constancy is not a mistake, but a clue. And once that question is taken seriously, the old theatre begins to change shape. The stage is no longer just a place where events occur. The clock is no longer a detached overseer. They begin to move toward one another, quietly at first, as if the universe has decided that what looked like two independent pieces of the set were really parts of the same construction all along. That is where things become much more interesting, because the next step is not merely to polish the old view, but to replace it with one in which space and time stop behaving like separate fixtures and start acting like a joined structure, which is precisely where Einstein enters and starts rearranging reality with the calm confidence of a man who appears to have noticed that the room was built wrong from the beginning. By the time Albert Einstein entered the story, physics was in an awkward position that did not always look awkward from the outside. On the surface, things seemed impressively stable. Newtonian mechanics still described the motions of ordinary objects with tremendous success. Engineers were not losing sleep over the motion of trains. Astronomers were not throwing telescopes into lakes. The old framework still handled most of the visible world with a calm authority that had earned it deep trust. Yet tucked inside that confidence was a growing problem. Light was not behaving the way the older picture said it ought to behave, and the more carefully people measured it, the less willing it seemed to cooperate. This matters because science often changes not when everything goes wrong, but when one thing refuses to fit. Most of the structure can remain solid and useful, and still one stubborn detail can begin to pry the whole frame apart. Light became that detail. According to the physics of the time, if you measured the speed of something while moving toward it or away from it, you should get different results depending on your own motion. That is how ordinary things behave. If you're running toward a tossed ball, the ball reaches you differently than if you're running away from it. If you walk through falling rain, the rain feels different than if you stand still. Motion changes what you measure. That was not a controversial principle. It was woven into common sense and classical mechanics alike. But the speed of light did not seem to play by those rules. Measurements kept implying that everyone got the same result. Whether the source moved, whether the observer moved, whether the whole arrangement sat still or rushed along, light kept offering the same speed. It was as though the universe had quietly inserted a fixed number into reality, and then dared everyone to explain it without breaking everything else. That fixed speed was not merely a curiosity. It threatened the old agreement between space and time. If the speed of the light stays constant for everyone, then the measurements of distance and duration cannot remain universal in the old way. Something has to adjust, and that something turns out to be both. Einstein, still a young man and not yet the figure whose hair alone would later inspire generations of people to trust him with cosmic matters, took the strange behaviour of light seriously. He did something that sounds obvious only after someone else has done it. Instead of trying to protect the old picture at all costs, he asked what the world would have to be like if the speed of light truly were the same for all observers. Not approximately the same, not usually the same, the same. This required a willingness to step away from intuition, because intuition had been trained in a slower world. Human common sense is built from walking, falling, throwing, driving, waiting, and aging on a medium-sized planet at very modest speeds. It is useful, but it is provincial. Einstein understood that if physics and intuition disagree, physics gets the last word. His first great move was special relativity, and the name special does not mean minor or decorative. It simply means the theory deals with a specific set of conditions, namely observers moving at constant speeds without the complication of gravity. Within that setting, Einstein began with two basic commitments. First, the laws of physics should be the same for observers moving uniformly relative to one another. Second, the speed of light in empty space should be the same for all such observers. These ideas sound manageable until you follow them to their consequences, at which point reality starts rearranging itself with unnerving calm. The older Newtonian world assumed there was a single universal time ticking away behind all events. If two things happened at the same time for one observer, they happened at the same time for everyone. That belief feels so natural that most people do not even notice they are holding it. If lightning strikes two trees at opposite ends of a field, either the strikes were simultaneous or they were not. It sounds like the sort of thing the universe ought to settle decisively, preferably without encouraging arguments on railway platforms. But Einstein showed that simultaneity itself depends on the observer's motion. This is one of the true turning points in the history of thought, and it is worth slowing down for it. Imagine a long train moving smoothly along a track. A person stands at the midpoint inside the train. Another person stands on the platform as the train passes. Suppose lightning strikes the front and back ends of the train. For the observer on the platform, if the strikes are equally distant, and the light from both reaches the midpoint at the same instant, then the strikes were simultaneous. Fair enough. But now consider the observer inside the moving train. Since that observer is moving toward the place where one flash originated, and away from the place where the other flash originated, the two flashes do not arrive together. Because the speed of light is the same in all directions for both observers, the person on the train concludes that the strikes were not simultaneous. Neither observer is making a mistake. That is the disturbing part. There is no hidden master clock waiting backstage to tell us which one deserves a gold star. Simultaneity is not absolute. It belongs to the relation between the observer and the events. Once that happens, the neat separation between space and time begins to collapse. If different observers carve up reality into different slices of what counts as now, then time is no longer a universal river flowing identically for all. It has become entangled with motion and position. This was not just a philosophical inconvenience, it had measurable consequences. If time is not universal, then moving clocks do not stay in perfect agreement with resting ones. If simultaneity depends on motion, then distances measured along the direction of motion cannot remain fixed in the old way either. To preserve the constancy of light, time dilates and lengths contract. These phrases can sound technical and remote, but the core idea is simple enough. The faster you move relative to someone else, the more your measurements of time and space differ from theirs. A moving clock runs differently. A moving length measures differently. These are not illusions caused by bad instruments. They are features of reality. It is easy to underestimate how radical that is. Up to this point, most people assumed that a clock was just a clock. If it was well made and properly set, it tracked the same underlying time everyone shared. A ruler was a ruler. If it was not bent or broken, it gave the true length of a thing. Einstein showed that this confidence had limits. Clocks and rulers are not merely passive readers of a pre-existing universal backdrop. Their readings depend on motion because motion affects the structure within which space and time are defined. That is what makes the change so profound. It is not that observers are sloppy, it is that the world is built this way. The result was not chaos. Einstein did not replace one tidy picture with a random disorder. He replaced it with a deeper order, one that looked stranger only because it was more accurate. There were still rules, still invariants, still precise relationships. But what remained fixed was no longer space by itself or time by itself. The fixed structure was something more unified. Space and time had to be treated as different aspects of one framework. This is where the stitching really begins. Einstein himself did not initially use the language of space-time in the most developed form we now know, but his theory made it necessary. A few years later, Hermann Minkowski, Einstein's former mathematics teacher, gave this necessity a more complete geometrical expression. He declared that space by itself and time by itself were fading into mere shadows, and that only a kind of union of the two would preserve independent reality. That statement can sound grand in a lecture hall, but it deserves its reputation. It named the deeper change. The universe was not built from separate coordinates of where and when that could be shuffled independently. It was built from events situated in a four-dimensional structure. 3 dimensions of space, 1 of time, joined into space-time. That does not mean time became just another ordinary direction like left or right. There are important differences, and those differences matter enormously. But it does mean that a physical event is best described as a location in space-time, not merely a point in space plus a moment attached as an afterthought. If you ask where something happened, you have not finished the job until you say when. If you ask when something happened, you have not finished until you say where. The two belong together in the most literal physical sense. This new picture solved the problem of light not by making light more ordinary, but by making space and time less independent. The speed of light stays constant because the universe adjusts measurements of distance and duration depending on the observer's state of motion. That is why 2 observers moving differently can both measure the same speed for light without contradiction. They are not working within a rigid common grid of space and a universal common clock of time. They are moving through space-time in different ways, and the geometry of that space-time determines how their measurements relate. Once this idea is accepted, many old assumptions begin to loosen. The old notion of a single worldwide present becomes difficult to maintain. The idea that all clocks should agree if they are simply accurate enough begins to fade. The confidence that motion happens in a passive arena gives way to the understanding that motion is part of the geometry of the arena itself. You do not simply move through space while time ticks elsewhere. Your motion affects how space and time are measured together. This also changes how we think about the world line of an object, though even that term can sound more intimidating than it is. Imagine the history of an object, not as a series of separate snapshots, but as a continuous path through space-time. A person standing still in a room is still moving through time, tracing a path. A person walking across the room traces a different path. A planet orbiting a star traces another. Light itself traces a path with special properties that reveal the deep structure of the whole framework. Once you think this way, the universe stops looking like a stage where actors move from place to place under an independent clock. It starts looking like an immense web of trajectories within a shared geometry. There is a tendency when talking about Einstein to make the story feel as though one brilliant person simply thought hard enough and bent the universe into a new shape. That version is a bit too clean. The problems were already present. Many physicists had been wrestling with the contradictions surrounding light and motion. What Einstein did with unusual clarity was refuse to preserve old intuitions that no longer fit the evidence. He took the symmetry of physical law seriously. He took the behavior of light seriously. And he followed the logic where it led, even when it pointed away from universal time and absolute space. That willingness matters because science does not merely accumulate facts. It also requires people to notice which ideas have become assumptions and ask whether nature actually signed off on them. The separation of space and time had become more than a working model. It had become a habit of thought. Einstein broke the habit. He showed that what felt natural was not fundamental. That is one of the reasons his work had such a philosophical impact beyond physics. It told people that the deepest structure of reality might not align with the categories our minds find comfortable. And still, special relativity was only the beginning. It dealt with motion at constant speeds, but it did not yet bring gravity into the picture. Gravity in the Newtonian view was a force acting across space. Objects pulled on one another over distance while time remained a separate steady background. Einstein would eventually go further and show that gravity itself is tied to the geometry of space-time. That later step is so famous now that it can overshadow how astonishing the first step already was. Before gravity could be reimagined, The old rigid frame of space and time had to be replaced with a stitched structure in which motion and measurement were inseparable. One of the quiet triumphs of Einstein's achievement is that it did not merely introduce exotic effects for extreme cases. It explained why the old picture works so well when speeds are small compared with the speed of light. In that ordinary limit, the strange effects become tiny. Time differences between moving observers are minuscule. Length changes are negligible. Simultaneity disagreements are too small to notice in daily life. Newton's framework survives as an excellent approximation, which is exactly what a good deeper theory should provide. It does not make ordinary life unrecognizable. It explains why ordinary life looks simpler than it really is. That is also why the theory feels so unsettling. We live in a world where the deeper structure hides politely most of the time. If every bus journey visibly altered clocks and every brisk walk noticeably changed the length of hallways, people would have discovered relativity while trying to get to market. Instead, the universe keeps its deeper geometry subtle at human scales. We needed careful experiments, sharp mathematics, and someone willing to doubt the obvious. Minkowski's geometrical reformulation helped many physicists see what Einstein's work truly implied. It was not just that clocks slow down and rulers shorten in certain circumstances. Those are consequences. The deeper point is that space and time are coordinates within one structure, and physical laws look cleaner and more natural when written that way. The stitching was not decorative. It was structural. Without it, the theory becomes a pile of odd corrections. With it, the whole picture gains coherence. This is also why the phrase spacetime deserves to be taken seriously and not treated as a bit of physics branding. It is not space plus time in the casual sense that a sandwich is bread plus filling. It is a union in which neither piece keeps its full old identity. Space is no longer an independent stage. Time is no longer a separate cosmic clock. Each helps define the other. Each loses meaning when isolated from the whole. That is the real stitching. Einstein's contribution was not simply to say that space affects time or time affects space in particular situations. It was to open the door to the realization that reality is built from their union in the first place. Once you accept that, familiar ideas begin to look newly fragile. Rest becomes relative. Distance becomes observer-dependent. Duration becomes observer-dependent. Even the order of events can shift in limited ways depending on motion, provided no signal needs to travel faster than light. The universe remains lawful, but the laws are written into a deeper geometry than earlier generations suspected. It is a world where the structure connecting events matters more than the old notions of universal position and universal time. There is something almost practical in the way Einstein approached this, despite how strange the results sound. He did not begin by trying to be mysterious. He began by demanding consistency. If the laws of physics are to be the same for all observers moving steadily relative to one another, and if light really does have the same speed for all of them, then the measurements of space and time must change together. In that sense, the stitching was forced by logic. The universe was not being romantic, it was being precise. Of course, for human beings, precision of that kind can feel almost rude. We like our present moment nicely shared. We like the idea that somewhere there is a universal now holding everything together like a tidy spine. We like the thought that time passes the same way for everyone, and that distance is simply waiting to be measured correctly. Einstein took those comforts, thanked them for their service, and showed them to the door. In their place, he offered something richer, though less immediately comforting. Reality is not less real because space and time are joined. It is more subtle, more exact, more demanding of us. And the joining did not end with fast motion. Once Einstein turned to gravity, the stitching became even deeper. Space-time would no longer be a flat arena in which paths merely differed by motion. It would curve. Massive bodies would shape it. Clocks would run differently, not only because of speed, but because of gravity itself. Distances and durations would respond together to matter and energy. the union of space and time would stop being a clever reinterpretation of motion and become the central architecture of the cosmos. So when people speak of Einstein's great stitching of space and time, they are naming a real shift in how the universe had to be understood. The old picture treated space and time like neighbouring departments. Einstein revealed that they belong to the same building, share the same foundations, and cannot be renovated separately. And once that is clear, the next thing to face is how motion itself changes what observers measure, because the moment space and time are stitched together, moving through the world no longer leaves distance and duration untouched. Once space and time have been stitched together, motion can no longer remain the simple thing it used to be. In the older picture, movement was almost innocent. An object changed its place while time flowed evenly in the background, untouched and impartial. A train crossed the countryside, a planet circled a star, a person walked from the kitchen to the front door, and none of that seemed to require any change in time itself. Motion happened inside the world, but it did not appear to change the framework of the world. Einstein showed that this comfort was too generous. Once space and time are understood as part of one shared structure, motion does not merely tell you how fast something travels through that structure. Motion changes how different observers divide it into distances and durations in the first place. That is the key point, and it is worth sitting with before anything else. Motion does not just alter what you see in the loose everyday sense. It changes what counts as a length and what counts as an interval of time when measurements are compared between observers moving differently. This is not about faulty eyesight, bad clocks, bent rulers, or people having strong opinions on trains. It is about the geometry of space-time itself. If two observers are moving relative to each other, they do not carve space-time into space and time in exactly the same way. One observer's distance is not automatically the other observer's distance. One observer's duration is not automatically the other observer's duration. These differences are not mistakes. They are reality behaving according to a deeper order than common sense first suggests. It helps to begin with a very ordinary instinct. Suppose you are standing beside a road and a car passes by. You naturally imagine that both you and the driver share the same time while disagreeing only about position and speed. The driver is moving relative to you. You're standing still relative to the ground. Perhaps you will assign different coordinates to the car's location at a given moment, but surely a second is still a second for both of you. Surely the car's length remains the car's length no matter who measures it. In daily life, that assumption works beautifully. The differences are far too small to notice. If you compare your wristwatch with the driver's after a short trip, you will not discover anything dramatic. If you measure the length of the car in a parking lot and then as it rolls past, it will not appear to shrink in any way that would trouble the manufacturer. But that calm agreement depends on the fact that everyday speeds are tiny compared with the speed at which relativity begins to reveal itself clearly. The deeper rule is not that motion leaves time and length untouched. The deeper rule is that motion changes them only by amounts so small in daily life that the changes hide beneath ordinary measurement. This is one of the universe's better disguises. It allows us to grow up inside an approximate world and mistake the approximation for the whole truth. To see what is really happening, physicists often turn to thought experiments because they strip away distractions and expose the structure underneath. One of the simplest involves a light clock. Imagine a clock built from two mirrors facing each other, with a pulse of light bouncing up and down between them. Each round trip of the light marks a tick. It is a very clean kind of clock because its behaviour depends directly on light, and light is precisely what forced the old view of space and time to be abandoned. Now picture this clock resting inside a moving train. To the passenger on the train, the light simply travels straight up to the top mirror and straight back down again. The tick is straightforward, but to someone standing on the platform watching the train pass, the light does not follow a straight up and down path. Because the train is moving sideways while the light bounces, the platform observer sees the light trace a diagonal path, longer than the path seen by the passenger. The light has farther to travel between ticks. Here the old universe would shrug and say that is fine, The platform observer is simply seeing a longer path, and therefore perhaps light is moving differently relative to the train and the platform. But Einstein's universe refuses that escape route because the speed of light must be the same for both observers. If the platform observer sees the light travel a longer path, then the only way for light to keep the same speed is for more time to pass between ticks. The moving clock must run slower relative to the platform observer, not because anything is wrong with it, not because it is damaged by travel, but because motion itself changes duration. This is time dilation, and few phrases in physics sound more theatrical while also being frustratingly accurate. A moving clock, as judged from another frame of motion, ticks more slowly. Every process tied to that clock slows accordingly. If it is a mechanical clock, its gears advance more slowly. If it is an atomic clock, its internal rhythm takes longer. If it is a heartbeat, a pulse, a chemical reaction, a strand of hair attempting to grow with quiet determination, all of it proceeds more slowly relative to the observer for whom the system is moving. It is very important not to turn this into a simple illusion. People sometimes hear about time dilation and imagine it is only a matter of appearance, as though the moving observer is secretly normal while everyone else is merely confused by perspective. But relativity is more democratic than that. From the moving observer's point of view, it is the other person who is moving, and their clocks are the ones that run differently. This mutuality can feel impossible at first. How can each observer find the other clock slow? The answer lies in the fact that simultaneity is not shared. They are not comparing clocks against one universal background. Each is using their own slicing of space-time into space and time, and those slicings are not identical. Once that is accepted, the apparent contradiction softens. Strange as it sounds, both can be correct within the structure of relativity. This alone changes the meaning of motion. In the old picture, motion altered only where something was at different moments. In the new picture, motion changes how those moments themselves are measured. It is no longer enough to ask where something is and when something is, as though those questions can be answered independently of who is moving relative to whom. Motion reshapes the measurement of duration, and if motion can alter duration, it can alter distance as well. These two effects are partners. They do not arrive separately. To preserve the deeper structure of space-time, changes in time come with changes in length. This is where length contraction enters, another phrase that sounds like it belongs in a lecture delivered by a patient person, with a blackboard and a tie slightly askew. The idea is that an object moving relative to an observer is measured to be shorter along the direction of motion than it is in its own rest frame. Again, this is not a trick of vision. It is not that the moving object looks squashed the way a fast photograph might blur. It is that the measured distance between its front and back, when defined carefully in the observer's frame, comes out smaller. The reason is tied once more to simultaneity. To measure the length of a moving object, you must determine where its front and back are at the same time, but what counts as the same time depends on your state of motion. Different observers therefore disagree in a very precise way about the length of the same moving object. This can feel almost rude from the universe. We're used to thinking of the size of a thing as among its most stable qualities. A ladder is a ladder, a train is a train. A loaf of bread, though suspiciously smaller than last year's loaf while somehow costing more, still seems like the sort of object whose length ought not to depend on who is walking past it. Yet relativity says otherwise. The length along the direction of motion is not absolute. It belongs to a particular frame of measurement. There is a well-known thought experiment involving a pole and a barn that captures the oddness. A runner carries a long pole toward a barn. In the barn's frame, the pole is moving very fast and therefore contracts, so at one moment it can fit entirely inside the barn. In the runner's frame, the barn is the thing that is moving, so the barn is the structure that contracts, and the pole remains too long to fit. Both descriptions can be consistent because the question of whether the pole is entirely inside the barn at one time depends on what counts as one time, and that depends on the frame. The details become wonderfully slippery, and one begins to suspect that reality enjoys these moments more than we do. The important thing is not the pole or the barn themselves, it is the lesson. Motion changes distance and duration together because space and time are not separate containers. They are linked in such a way that preserving the universal role of light forces them to compensate for each other. A longer path for light in one frame means a longer time in that frame. A different slicing of events into simultaneous moments means a different measured length. These are not optional corrections. They are the cost of keeping the laws of physics the same for all observers and the speed of light constant. One of the most famous consequences of this union is the so-called twin story. Imagine two twins. One remains on Earth while the other travels in a spacecraft at tremendous speed and later returns. According to the traveller's onboard clock, less time passes than on Earth. When they reunite, the travelling twin is younger. This is not because space is good for the skin or because the home twin got tangled in unusually stressful paperwork. It is because the traveller followed a different path through space-time, one involving enormous speed and a turnaround, and that path contains less proper time. That phrase, proper time, sounds technical, but it captures something important. It is the time measured along the path actually lived by the traveller, not an abstract universal time, because relativity has no use for such a thing. Instead, each object carries its own history through space-time, and the elapsed time along that history can differ from the elapsed time along another. In that sense, time is not something all beings simply bathe in equally. It is part of the path. Motion changes the path, and the path changes the experienced duration. This has been confirmed in the real world many times over. Atomic clocks carried on aircraft do not stay perfectly aligned with clocks that remain on the ground. Particles created high in the atmosphere survive longer when rushing toward Earth than older expectations would suggest, because from our perspective their internal clocks are running more slowly. These are not speculative consequences saved for distant galaxies. Relativity appears in laboratories, in particle physics, in satellite systems, in precision timing. The universe has signed its name to this idea repeatedly. It is also worth noticing how these effects reveal a new kind of unity between space and time. In the older world, distance and duration were separate measures taken against independent backdrops. A length belonged to space, an interval belonged to time. Once motion changes both, their separation becomes less natural. A thing does not merely have a location and then happen to persist through time. It traces a path through space-time, and what different observers call its length and its duration depend on how they stand in relation to that path. This is why motion does not simply add a detail to the story, it changes the grammar of the story. In ordinary speech, we tend to imagine ourselves moving through space as time passes. Relativity invites a different picture. We're always moving through space-time, and the way that motion divides between the spatial and temporal aspects depends on our state of motion. That is a careful statement, but its intuition can be approached gently. If one observer moves very little through space relative to a given frame, they move in a way that carries them more deeply through time in that frame. If another moves very rapidly through space, the temporal side of their motion changes accordingly. The balance shifts. This is one reason the speed of light sits at the center of the theory. Light follows a limiting behavior that reveals the architecture of the whole framework. Nothing with mass can be pushed to move through space exactly as light does. The closer you get, the more dramatic the effects on time and distance become. Clocks slow more noticeably. Lengths contract more severely. The old common sense picture begins to fail more openly. At ordinary speeds, relativity whispers. Near the speed of light, it starts speaking clearly. And still, none of this means that the world becomes subjective in the loose sense. Relativity is not a permission slip for saying anything goes. Observers may disagree about distances and durations, but they do so according to strict laws. The disagreements are structured, calculable, and consistent. There remains a deeper order underneath, and that order lives in space-time itself. Different observers are not inventing private realities. They are measuring the same reality through different motions within the same geometric framework. There is something almost humbling in that. Human beings often want certainty in the form of a single shared clock and a single shared ruler. Relativity says you may have consistency without universality. You may have law without a cosmic master schedule. Reality does not owe you one privileged viewpoint. It offers instead a disciplined harmony among many viewpoints, tied together by the geometry of space-time and by the stubborn constancy of light. It also changes how we think about travel, aging, and causality. If motion affects duration, then journeys are not merely a matter of covering distance. They are ways of tracing different temporal histories. If motion affects length, then distance itself is not as fixed as it once seemed. The farther physics moved from everyday intuition, the more it became clear that space and time were not passive bookkeeping categories. They were part of the active structure governing what could happen and how it could be measured. That realization can feel a little chilly at first because it removes some of the familiar furniture. The room no longer has one central clock on the wall. The floorboards are not marked with permanent universal lengths. Yet in place of that older comfort comes a more remarkable kind of coherence. The behaviour of moving clocks, moving rods, fast particles, and travelling twins all become parts of one picture. Motion changes distance and duration because motion changes how an observer's frame slices the shared fabric of space-time. There is nothing arbitrary about it. It is the natural expression of the union Einstein uncovered. And all of this rests on one demanding fact that keeps returning like a patient but persistent guest. Light does not adjust itself to our expectations. It is the old Newtonian expectation that had to bend. Once the speed of light is taken seriously as the same for all observers, space and time must give way together. That is why motion reshapes both. Not because motion is magical, and certainly not because the universe enjoys making train journeys philosophically inconvenient, but because the speed of light acts as the organizing principle that forces the geometry of space-time to reveal itself. So when we say motion changes distance and duration, we are not adding a curious side effect to physics. We are naming one of the clearest signs that space and time are inseparable. A moving object is not simply elsewhere at a later moment. Its very measurements of elsewhereness and laterness depend on the motion involved. The old stage and clock cannot survive that intact. In their place stands a universe where what you measure depends on how you move, and where the deepest reason for that dependence lies in the one thing that refuses to change from one observer to the next, which is precisely where the story must go next. There is a reason light keeps returning to the centre of this story. It is not merely bright, fast and useful for finding your slippers in the dark. It is the thing that forced physics to stop treating space and time as separate comforts and start treating them as a one-joined reality. Before Einstein, the idea of absolute time still felt deeply secure. Even if space could be measured differently from place to place, time seemed untouchable. There might be confusion over calendars, faulty clocks, or whether a meeting scheduled for past means past exactly or past in the more imaginative social sense. But beneath all that, people assumed there was one true time flowing through the universe. Clocks might track it better or worse, yet the thing itself remained steady, universal, and independent of who was measuring it. That picture lasted so long because it fit ordinary life beautifully. If you and I stand in different rooms and compare watches later, we expect them to agree, provided neither of us bought ours from a suspicious market stall near a railway station. If we watch a football fly through the air, we expect to disagree perhaps about its position or speed depending on where we stand, but not about the time through which it moved. Time seems like the one part of reality that should not need negotiation. It passes for everyone, everywhere, with calm indifference. It does not seem like the sort of thing that should care whether you're standing still, walking, riding a train, or being dragged through the airport by a suitcase that has suddenly become much heavier than when you packed it, and then light arrived and refused to behave. The problem did not begin with Einstein. It had been building for some time. During the 19th century, physicists developed a powerful theory of electricity and magnetism, and in that theory light emerged as an electromagnetic wave. This was a major triumph. Light was no longer some mysterious heavenly essence. It became part of the same physical world as sparks, magnets, and electric currents. Better still, the theory predicted a specific speed for light. That was impressive, but it also opened a difficult question. A wave usually travels through something. Sound travels through air. Water waves travel through water. So through what exactly was light waving? The answer many physicists favoured was the ether, an invisible medium thought to fill all of space. It had to be everywhere, because light from the stars reaches us through what appears to be empty space. The ether would provide the background through which light moved, just as air provides the background for sound. It was a sensible idea by the standards of the time, though one suspects the ether itself, if consulted, might have objected to being assigned so much responsibility without the courtesy of direct evidence. Once the ether was proposed, another expectation followed naturally. If Earth moves through this medium as it travels around the Sun, then our motion through the ether ought to affect how light behaves when measured in different directions. Imagine moving through falling rain. You feel it strike you differently depending on your direction of motion. If the ether were real, something similar should happen with light. Physicists should be able to detect Earth drifting through the ether by measuring slight differences in the speed of light along different paths. That was the hope behind one of the most famous experiments in the history of science, carried out by Albert Michelson and Edward Morley. Their setup was ingenious. It split a beam of light into two paths at right angles, then brought them back together to see whether one beam had been delayed relative to the other by Earth's motion through the ether. If Earth was ploughing through this invisible medium, then light travelling in one direction should behave slightly differently from light travelling in the other. The result should have been detectable. It was not. That failure was not a small inconvenience. It was the sort of result that sits in the corner of the room and refuses to leave. The expected evidence of motion through the ether simply would not appear. Light kept acting as though there were no special background medium setting a preferred state of rest. This was deeply unsettling because the older view of space and time relied in spirit on the idea that there was some stable framework beneath all motion. Even if people disagreed about where something was, they assumed there was a fact of the matter about who was really moving and through what. The ether seemed like a way to preserve that intuition for light. And yet nature declined the invitation. Physicists, being sensible people who do not immediately burn down a successful worldview because one experiment goes badly, tried to save the old picture. Perhaps matter moving through the ether changed shape in just the right way to hide the effect. Perhaps the measuring apparatus contracted slightly. Perhaps the ether had more peculiar properties than anyone realized. These were not ridiculous suggestions. In science, patching a theory is often wise before replacing it. But the deeper issue remained. The equations of electromagnetism seemed to treat the speed of light as fixed, while the old Newtonian world expected measured speeds to depend on the observer's motion. Einstein's brilliance lay in his willingness to stop patching and start rethinking. He took the behaviour of light at face value. What if the speed of light in empty space is the same for every observer moving uniformly, no matter how the source or observer is moving? That idea sounds almost harmless when spoken quickly, but it detonates the old view of time. Because if light's speed must be the same for everyone, then the usual way we add velocities together no longer works across the board. And if the old way of combining motion breaks down, then space and time cannot remain absolute. It is important to see why. Suppose you are standing still and shine a flashlight. Common sense says the beam races away from you at the speed of light. Now imagine you're on a very fast train and shine the same flashlight in the direction of motion. In the old world view, one would expect the light's speed, as seen by someone standing beside the tracks, to be the speed of light plus the speed of the train. That is how ordinary things behave. Throw a ball from a moving cart and a stationary observer sees the ball's speed as your throwing speed plus the cart's speed. Simple enough. But light refuses to do this. The observer by the track still measures the beam moving at the speed of light, not a bit more. The passenger on the train measures the same thing. Both get the same result. At first, this feels impossible. Surely one of them must be mistaken. But relativity insists neither is. The price of keeping light's speed fixed is that measurements of space and time must change. If two observers are both to measure the same speed for light, despite moving relative to each other, then their assessments of distance and duration cannot be identical. One or both must give way, and in fact both do. That is the beginning of the death of absolute time. The first casualty is simultaneity. Before Einstein, it seemed obvious that if two events were simultaneous, then they were simultaneous for everyone. The universe, one assumed, kept a single official record. If two clocks strike noon at different ends of a field, they either did so together or they did not. Yet light makes this certainty impossible to maintain. Observers moving relative to one another will not always agree on whether two separated events happened at the same time, and if they cannot agree on that, then there is no universal presence stretching cleanly across the cosmos. This point is so important because most people do not realize how much of their worldview depends on the idea of a shared now. We imagine the universe as though everyone is occupying the same great slice of time at once. Somewhere out there, distant stars, passing trains, late-night kitchens, hospital corridors, and other people brushing their teeth are all part of one cosmic moment called now. Relativity says that this picture is not fundamental. Different observers, moving differently, carve reality into different sets of simultaneous events. There is no single universal sheet of presentness laid over everything. That is a very strange thing to accept. It means the order of distant events is not always as fixed as common sense imagined, at least not when no causal influence can connect them faster than light. The universe does not come with one master clock announcing the same now to all observers. What survives instead is the space-time structure, within which different observers make different but lawful divisions between space and time. This is the deeper reason absolute time dies. It is not merely that clocks run at different rates under certain conditions, though they do. It is that the very idea of a single cosmic time flowing identically for all becomes incompatible with the constancy of light. There can still be time for each observer, and there can still be consistent relationships among observers, but there is no longer one universal temporal river carrying everyone at the same pace. Time dilation follows from this. If a moving clock is measured by a stationary observer, it ticks more slowly. That phrase can sound like a magic trick the first few times you hear it, but it is one of the most tested consequences of relativity. The key is that a clock is any process that marks time, a pendulum, a quartz vibration, an atomic oscillation, the decay of a particle, even your own biological aging. If the clock is moving relative to you, and if light keeps its constant speed, then the time measured by that moving clock must stretch relative to yours. Less time passes on the moving clock between comparable events. This is not speculation. It has been confirmed in countless ways. Atomic clocks flown on aircraft end up out of step with clocks left on the ground. Particles created high in the atmosphere live longer, from our perspective, when racing toward Earth at enormous speeds, than they would if their internal clocks matched ours exactly. Satellites must account for relativistic effects to keep navigation systems accurate. Without these corrections, modern positioning technology would drift into embarrassing uselessness with surprising speed. Your phone would confidently direct you into canals, hedges, or someone else's driveway, and while that might be entertaining once or twice, it would not count as scientific progress. There is a temptation to think that all this only matters at extreme speeds, and therefore belongs to astronauts and physicists, not to ordinary life. In one sense, that is true. At human speeds, the effects are tiny. A bicycle ride will not noticeably extend your youth. Sprinting to catch a bus, however heroic it may feel, will not alter your aging in any way that improves your skincare prospects. But the principle matters enormously, because it tells us what time is and what time is not. Time is not a universal backdrop through which events pass independently of motion. Time is bound up with the observer's path through space-time. This changes how we think about clocks themselves. A clock is not revealing a hidden master time that exists the same way everywhere. A clock measures the time along its own path. Two clocks that follow different paths through space-time can later disagree, and neither is wrong. They have lived different temporal histories. This is a profound shift. In the old world, disagreement between good clocks meant error. In the relativistic world, disagreement can mean geometry. The speed of light also sets a limit that further transforms time. Because no signal can travel faster than light, not all parts of space-time can influence one another arbitrarily. Causes and effects are constrained. There are events that can affect you and events that cannot, depending on their place in space-time relative to your own position. This structure gives the universe its causal order. Light is not just another fast thing flying about. It is the thing that marks the boundary between what can be connected and what cannot. In that sense, the speed of light is woven directly into the architecture of reality. That architecture is precisely what absolute time cannot survive. Absolute time assumes a universal ordering independent of motion and position. Relativity replaces that with a more delicate but more accurate order, one defined by space-time intervals and causal structure. Some events are definitely before others, because a signal could pass between them. Some are definitely after. But for events too far apart to influence each other within the light limit, the order can depend on the observer. That does not make the universe chaotic. It makes it more subtle than our earlier picture allowed. There is also something quietly humbling about how this change came about. Absolute time was not destroyed by some vague philosophical complaint. It was undone by careful attention to measurement, consistency, and the behavior of light. The old intuition that time must be universal simply could not be preserved once the constancy of light was taken seriously. This is often how science advances, not by seeking strangeness for its own sake, but by following ordinary honesty about evidence until old certainty gives way. And yet, even as absolute time dies, something new and more durable takes its place. Space-time provides a unified structure in which all observers can relate their measurements consistently. They may disagree about durations and distances, but they agree on the deeper rules connecting those disagreements. This is crucial. The death of absolute time is not the death of order. It is the death of one kind of order in favour of a deeper one. You can think of it this way. In the old picture, reality seemed to come with one perfect clock mounted somewhere in the universe, silently governing everything. In the new picture, there is no such clock. Instead, there is a shared space-time geometry, and each observer carries their own valid clock through it. What survives is not one universal time, but the lawful relation between many local times. That may sound less comforting at first, but it is far more remarkable. The universe does not need a central timetable to remain coherent. This is also why Einstein's work feels so transformative even now. It did not merely add corrections to an older theory, it changed the very question. Instead of asking how things move through absolute space during absolute time, we ask how events are arranged within space-time, and how different observers moving relative to one another relate their measurements. Light forced that change because its speed refused to bend to older expectations. It stood there, immovable in value, while our assumptions buckled around it. And that is perhaps the most elegant part of the whole affair. Light did not announce itself with drama. It simply behaved with stubborn consistency. Everyone measured the same speed, and from that one fact an entire worldview had to be rebuilt. The great cosmic clock, once imagined to tick the same for all, was quietly dismantled. In its place came moving clocks, local times, relative simultaneity, and a universe where space and time could no longer be pried apart without ruining the whole design. So when we speak of the speed of light and the death of absolute time, we are naming one of the most decisive turns in the history of thought. It is the moment physics stopped treating time as a universal background and began treating it as part of a joined structure that depends on motion, measurement, and the deeper rules of space-time. And once time has given up its old universal throne, gravity can no longer remain a simple force acting in a passive arena either. It too must be reimagined, because the next step is to see what happens when mass enters the story and begins to shape not just motion, but the very geometry of space and time together. Once time gave up its old role as a universal background, gravity could not remain what it had been in the older picture. Under Newton, gravity was a force that acted across space. Bodies pulled on one another from a distance. The Earth pulled the apple downward, the Sun pulled the planets inward, and the Moon was kept in orbit by that same invisible attraction. It was a brilliant framework and a deeply successful one. It explained an enormous range of motion with astonishing precision. But it still assumed that space was the stage and time was the clock. Gravity happened inside that arrangement. It did not change the arrangement itself. Einstein eventually realized that this could not be the full story. If space and time belong to one structure, then gravity should not be treated as a simple force acting within a passive background. It should have something to do with the shape of the background itself. That shift is one of the great turns in science. Gravity stopped being just a pull and became a clue. Mass and energy do not merely move through space-time, they help determine its geometry. And once that happens, the old idea of empty space as a quiet box waiting to be filled begins to fall apart. Space and time are not passive, they respond. To appreciate how radical that is, it helps to begin with a very familiar experience. If you're standing on the ground, you feel your weight. It feels obvious that gravity is pulling you downward. A dropped object falls. A glass slips from the counter and reminds everyone nearby that mornings can always get worse. Rain comes down. Fruit falls from trees. All of this seems to support the idea that gravity is a force dragging things toward the Earth. So Einstein needed a very good reason to doubt that picture, because ordinary life keeps voting for it every day. The reason came from a simple but powerful insight. All objects, regardless of their mass, fall the same way when air resistance is ignored. A hammer and a feather dropped in a vacuum do not race one another with dramatic unfairness. They fall together. Galileo had already helped make this point clear. The fact is so familiar now that it is easy to miss how odd it really is. In many situations, different objects respond differently to forces. Push a cart and a grand piano with the same effort and you will not get matching results. Yet gravity treats all falling bodies with a kind of strange equality. This suggested to Einstein that perhaps free fall is not ordinary forced motion at all. He followed that idea into one of the most famous thought experiments in physics. Imagine a person inside a closed elevator far from any planet or star. If the elevator is being pulled upward through space by a rocket, the person inside feels pressed to the floor. If they drop an object, it falls to the floor just as it would on Earth. Now imagine instead that the elevator is standing still on the surface of a planet with gravity. The same thing happens. The person feels weight. A dropped object falls. Inside the box, the two situations are locally indistinguishable. On the other hand, if the elevator is in free fall toward the planet, the person inside feels weightless. Objects seem to float beside them. For a brief time, free fall feels like gravity has vanished. This is the heart of the equivalence principle, and it is one of Einstein's deepest clues. Locally, being in free fall is like being free of gravity. Locally, being accelerated can mimic gravity. That is a very strange thing if gravity is just another force. But it makes much more sense if gravity has to do with the structure of space-time itself. A freely falling object is not being yanked away from its natural motion. It is following the natural path allowed by the geometry around it. The reason you feel weight while standing on Earth is not that gravity is doing something to you in the most basic sense. It is that the ground is preventing you from following the path you would naturally take through curved space-time. In a peculiar way, the falling object is the one behaving more naturally, and you standing still on the floor are the one being interrupted. That is a wonderfully unfriendly idea to spring on human intuition. We feel safe and settle when standing still. We imagine ourselves at rest and the falling object is the thing in trouble. Einstein flips that around. The object in free fall is following the straightest available path through curved space-time. You, held up by the floor, are being forced away from that path. The floor is what presses on your feet. That pressure is what you interpret as weight. Gravity, in this view, is not mainly a tug. It is geometry. Now, when physicists say geometry here, they do not mean schoolroom geometry with neat triangles, and someone insisting there is only one correct way to draw a circle. They mean the actual structure of distances, durations, and paths in the physical world. In a flat space-time, free objects move along the straightest possible routes. In curved space-time, those routes can bend relative to ordinary expectations. Objects then appear to fall, orbit, or accelerate not because an invisible hand is pulling them in the old sense, but because the space-time through which they move is not flat. A simple analogy often used here is the stretched rubber sheet, with a heavy ball placed on it. A smaller ball rolling nearby curves inward because the sheet is deformed. It is not a perfect analogy, because the sheet uses gravity itself to illustrate gravity, and that can feel like borrowing your own umbrella from the future. Still, it gives a useful hint. Massive objects change the shape of the surrounding structure, and other objects respond by moving along the paths available in that changed structure. The sun does not simply reach out and pull the Earth by an invisible string. The sun shapes space-time around it, and the Earth moves within that shaped space-time. This is why general relativity, Einstein's later and broader theory, is so powerful. Special relativity had already joined space and time. General relativity says that this joined structure is not rigid. It can curve, it can stretch, it can be shaped by mass and energy. The universe is not a fixed grid with events scattered across it like pins on a board. The board itself has become dynamic. That has enormous consequences. Planetary orbits are no longer understood as bodies being tugged through flat space by a force acting instantaneously across distance. They are understood as bodies following natural paths in curved space-time around a massive object. The Earth moves the way it does because of the geometry created by the Sun. The Moon moves the way it does because of the geometry created by the Earth. Light itself, despite having no mass, follows the curvature too. This was one of the great triumphs of Einstein's theory. Starlight passing near the Sun should bend because space-time there is curved, and observations during a solar eclipse confirmed that prediction. Light was not being pulled in the old simple sense. It was following the shape of the geometry. At that moment, gravity stopped being just about falling apples and orbiting planets. It became a property of the structure of reality. Massive bodies tell space-time how to curve, and curved space-time tells matter and light how to move. That summary is famous for a reason. It compresses an enormous conceptual revolution into a sentence simple enough to remember. Still, the sentence can sound smoother than the idea really feels. If space-time is what gets curved, then both space and time are affected. Not one, then the other as an afterthought. Both. This is where many people first realize just how deep Einstein's revision went. It is one thing to say space is curved. We can half imagine that. We picture warped distances, bent paths, strange routes around massive things. But time being affected by gravity is harder to absorb, because time still tends to feel private and steady. We imagine that a second is just a second, even if roads get crooked. Yet general relativity says that clocks run differently depending on gravity. A clock deeper in a gravitational field runs more slowly than one farther away. That is not philosophy, it is measurement. This effect is called gravitational time dilation. A clock near a massive body ticks more slowly relative to a clock farther from that body. If you place one clock at sea level and another high on a mountain, they do not stay perfectly in sync. The lower clock closer to the Earth and deeper in its gravitational field falls behind by a tiny amount. The effect is very small in everyday conditions, but it is real and measurable. Modern technology has to account for it. Satellites orbiting Earth experience gravity differently from clocks on the ground, and if those timing differences were ignored, systems that rely on precise timing would become inaccurate very quickly. That matters because it shows gravity is not merely a matter of things moving differently in space. Time itself is part of the story. A massive object changes not just the shape of paths through space, but the rate at which time passes. This is why space-time has to be treated as one thing. If space alone curved while time stayed untouched, the theory would fail. If time changed while space remained indifferent, the theory would fail in a different way. Gravity grips the shape of both at once. There is something almost practical in the way this new picture explains what Newton had described so well. Newton could calculate orbits brilliantly, but he treated gravity as an attraction acting across a fixed background. Einstein explains why those motions occur in the first place by changing the meaning of the background. The older equations remain an excellent approximation when gravity is not too strong and speeds are not too high. That is why Newton still works for bridges, projectiles, and ordinary planets well enough in many cases. But general relativity goes deeper. It tells us that what looks like force from the outside is often geometry from the inside. This also helps explain one of the small oddities that puzzled astronomers under Newtonian gravity. The orbit of Mercury did not line up perfectly with the old calculations. Most of it did, but there was a leftover mismatch that would not go away. General relativity accounted for that stubborn difference naturally. The space-time near the Sun is curved enough that Mercury's path shifts in a way Newton's older picture does not fully capture. It was a small discrepancy, but small discrepancies have a habit of changing science when they are honest enough to stay unresolved. Another consequence of curved space-time is that gravity does not travel as an instantaneous influence. In Newton's framework, gravitational attraction acted across distance, in a way that raised uncomfortable questions about how one body could affect another with no delay. Einstein's picture handles this more gracefully. Changes in the distribution of mass and energy alter space-time, and those changes propagate. If massive bodies accelerate in the right ways, they can generate ripples in space-time itself, called gravitational waves. For a long time, these were a theoretical prediction. Then they were detected directly, produced by massive cosmic events such as black holes spiraling together. The universe was found to be sending out wrinkles in its own geometry. That discovery matters here because it shows space-time is not just an idea used for calculations. It behaves physically. It can carry disturbances. It can be measured. It can ring in a sense when enormous events shake it. This is about as far from the old passive stage as one can get. The stage is now responsive, dynamic, and deeply involved in the drama. And yet, daily life hides most of this. On Earth, gravity feels steady enough that we call standing still normal. Time differences due to altitude are tiny. Light bending near ordinary objects is too small to notice. Curvature itself is subtle at the scales where people are mostly concerned with shopping lists, train schedules, and whether they remembered to answer that email. But subtle is not the same as absent. The deeper structure is there all the time. Even your own body lives within this framework. Your feet, being slightly closer to Earth's centre than your head, experience a very slightly stronger gravitational field, which means time passes just a little more slowly there. The difference is absurdly tiny, not something likely to transform your understanding of socks or shoes, but it is real. That is the unsettling charm of general relativity. It does not only belong to black holes and distant galaxies. It belongs to staircases, mountains, satellites, and the simple fact that clocks are affected by where they are. The stronger the gravity, of course, the more dramatic the effects. Near a very massive and compact object, space-time becomes so curved that ordinary intuition gives up almost immediately. Orbits become strange. Light bends dramatically. Time slows more severely. Near a black hole, these effects become extreme. From far away, an infalling clock appears to slow more and more. To the falling observer, things proceed normally in their own proper time, at least until conditions become very unpleasant in ways the brochure definitely forgot to mention. The point is not just that gravity is strong there. It is that space-time is shaped so intensely that the distinction between what space is doing and what time is doing becomes impossible to tease apart. This is why gravity's grip on space-time is not an optional extra in modern physics. It is the framework. Once Einstein made this move, gravity was no longer sitting beside space and time as a separate actor. It had become part of the story of what space and time are. Mass and energy do not merely occupy the universe. They participate in shaping the arena that defines motion, duration, and distance. That also changes the way we think about falling. In the older view, to fall was to be pulled. In the newer view, to fall freely is to follow the natural path through curved space-time. The sensation of weight comes from resisting that path. A person in orbit around Earth feels weightless, not because Earth has stopped affecting them, but because they are continuously falling in the natural way allowed by the geometry around the planet. They are not floating because gravity is absent. They are floating because gravity is geometry, and they are moving with it rather than being held against it. This is such a clean reversal of ordinary language that it deserves a moment of appreciation. We say astronauts are beyond gravity, but they are not. They are deeply within Earth's gravitational influence. They are simply in free fall, which general relativity identifies as the closest thing to natural inertial motion in a curved space-time. Meanwhile, the person standing firmly on the ground, who feels most secure and least dramatic, is the one being constantly accelerated upward by the ground, preventing them from falling. Physics can be wonderfully impolite that way. Once you accept all this, the title of our larger subject becomes even clearer. Space and time cannot exist independently in a world with gravity, because gravity does not act on one without the other. A massive object does not merely change distances while leaving durations intact. It does not merely change clock rates while leaving geometry of paths alone. It alters the full structure. Space is shaped, time is shaped, motion follows from that shaping. And that is why gravity has such a firm grip on the story. It is not just one physical effect among many. It is the place where the union of space and time becomes visible in the architecture of the universe itself. You cannot fully describe an orbit, a falling body, a beam of light passing a star, or the ticking of a clock near a planet unless you let gravity work on space-time as a whole. Once that becomes clear, another question follows almost immediately, because if gravity shapes both together, then bending space without bending time starts to look less like a serious possibility and more like a misunderstanding waiting to be corrected. By this stage, the temptation is to picture gravity as something that mostly wrinkles space, while time tags along behind it, mildly inconvenienced but not fundamentally involved. That is a very common halfway picture, and one can see why it happens. Curved space is easier to imagine. You can picture a path bending. You can imagine a straight route becoming a crooked one. You can look at an orbit and think perhaps the planet is simply following a curved track through a distorted spatial landscape. Time, on the other hand, still feels private and steady. It feels like the quiet part of reality, the thing that keeps going while everything else gets pushed around. So people often accept that gravity bends space, and only later discover that this is not enough. In Einstein's universe, you cannot bend space without bending time, because the two are not separate pieces that can be adjusted independently. They are parts of one geometry, and gravity grips the whole thing. The simplest reason is also the deepest. Motion in the universe is described through space-time, not through space alone. An object does not merely trace a route through locations, it traces a history. That history includes where it is and when it is there. If gravity changes the structure within which that history unfolds, then both the spatial and temporal sides of the structure must be involved. A bend in space alone would not tell clocks how to behave. A bend in time alone would not fully guide paths through the world. General relativity works precisely because it treats the geometry as one connected thing. It helps to begin with a familiar misunderstanding. Suppose someone says gravity makes the Earth go around the Sun because space around the Sun is curved. That is not wrong as far as it goes, but it is incomplete in a way that matters. If only space were curved and time remained universal and untouched, the motion predicted for real objects would not match what we observe. The orbiting Earth is not just moving through a bent arena while one master clock ticks in the background. The timing of motion, the rate of clocks, the meaning of straightness, and the structure of cause and effect are all altered together by the Sun's presence. The geometry that matters is not a shape drawn only in space, it is a space-time geometry. One way to see this is to think about freefall again. In general relativity, an object in freefall follows the natural path available in the curved geometry around it. That path is not defined only by spatial shape, it is defined in space-time. A falling apple is not choosing a route across a distorted three-dimensional map, while the universal clock watches from a safe distance. It is following the straightest possible history through a curved four-dimensional setting. If you tried to keep time absolutely fixed while curving only space, the very notion of what counts as the natural path would break apart from what clocks actually measure. You would be forcing motion and timing into two incompatible descriptions of the same event. Light makes this impossible to ignore. Throughout relativity, light acts like the stern supervisor of physical consistency. It keeps turning up and preventing people from cheating. The speed of light in empty space is not negotiable from one local observer to another. If gravity bends paths through space, and if light is to remain governed by the same local rule, then time must adjust as well. Otherwise, the relationship between distance and duration would no longer preserve the local behavior of light. You would have spatial distortions without the matching temporal distortions required to keep the structure coherent. This is one reason gravitational time dilation is not a decorative side effect. It is essential. Near a massive object, clocks run differently. A clock deeper in the gravitational field ticks more slowly relative to one farther away. If that were not true, the geometry would not describe the world correctly. Light would not behave in the observed way. Falling bodies would not move in the observed way. Signals sent between different heights in a gravitational field would not show the frequency changes they actually do show. The theory would lose its grip on reality. A good practical example comes from navigation satellites. These satellites orbit Earth far above the surface, where gravity is weaker than it is on the ground. Their clocks run differently because of that difference in gravitational environment. Engineers must correct for this. If they pretended space near Earth was curved in some useful sense but time flowed exactly the same on the ground and in orbit, the timing system would drift and positioning would fail. That is not a philosophical inconvenience, it is a measurable operational problem. Your map would become steadily less trustworthy, which may not sound like a cosmic crisis until you are trying to find a hospital, a train station, or the one cafe that promised to be open and has betrayed you. The point is that gravity reveals itself in the behavior of clocks just as much as in the behavior of paths. That already tells us that time is not merely accompanying the story. It is one of the main characters. There is another way to approach the issue, and it goes to the heart of what curvature means in Einstein's theory. In ordinary geometry, one can speak about the curvature of a surface like a sphere or a saddle. But general relativity does not merely curve surfaces inside a larger background. It changes the relationships by which distances and durations are measured in the physical world itself. Those measurements are tied together. A ruler tells you about space. A clock tells you about time. But the theory does not treat them as independent devices reporting on separate universes. Their readings are part of one metric structure. That word metric here simply means the rulebook for how separation is measured. Once gravity changes that rulebook, it changes both kinds of measurement. This is why the common rubber sheet analogy, while helpful in small doses, can become misleading if taken too literally. It encourages the idea that masses merely dent space, as though time were waiting politely off to the side. In reality, the full geometry is richer than a dented surface. It includes how long intervals last, how signals propagate, which events can influence which other events, how freely falling bodies age, and how light travels. If you try to picture only curved space, you miss the temporal architecture that makes the picture physically correct. One place where this becomes especially clear is the bending of light near massive bodies. In the early days after Einstein proposed general relativity, one of the celebrated tests involved starlight passing near the sun. The light appeared deflected. Now you might think that if space alone were curved, perhaps that would be enough. Light follows the bent route and there you are, but the full amount of bending predicted by general relativity depends on the combined curvature of space and time. A picture that distorts only time gets the wrong answer. A picture that distorts only space also falls short in the deeper interpretation. The actual deflection is a space-time phenomenon. The path of light responds to the full geometry. That is an important clue because light has no rest mass. If even light responds to the combined structure, then gravity is not simply about pulling on heavy things. It is about shaping the arena of paths and durations for everything. Light traces out the causal skeleton of space-time. It shows what can connect to what, which signals can travel where, and how events are related. If gravity changes that skeleton, then it cannot be modifying only spatial layout. It must be reshaping the temporal and causal structure as well. This leads naturally to the idea of local physics. General relativity says that in a very small region of space-time, one can always choose a frame in which the laws of physics look locally like those of special relativity. In that small enough neighbourhood, light still behaves locally as it should, clocks behave normally, and the geometry looks almost flat. But when you compare different regions, the curvature shows up. The fact that local flatness can be recovered only in space-time terms is crucial. You do not recover the physics by flattening space alone while leaving a separate universal time in charge. You recover it by flattening the full local space-time structure. That is what the theory actually says about the world. If that sounds technical, it can be softened without losing its meaning. Imagine walking around on a huge curved planet. In your immediate vicinity, the ground looks flat enough to stroll across without philosophizing. But over larger distances, the curvature matters. Now imagine that not only the ground, but your clocks also differ subtly from place to place, depending on where you are and how you move. That is closer to space-time, locally familiar, globally curved. You do not get the correct world by curving the floorboards while insisting the clocks remain absolutely the same everywhere. There is also a strong argument from causality. In relativity, the ordering of events and the possibility of influence are tied to the structure defined by light. This structure determines what can be the cause of what. If gravity acted only on space, leaving time completely untouched, then the causal order established through the propagation of light would no longer mesh correctly with the geometry guiding matter. You would have one structure trying to govern paths through space, and another trying to govern temporal sequence, and the two would not consistently agree. General relativity avoids this split by letting gravity shape the full causal fabric. Events are arranged in a geometry that tells both matter and light how to move and tells clocks how to tick. This is one reason black holes are such a dramatic example, though we're only just approaching them properly. Near a black hole, one does not merely have very curved space in the everyday sense. One has such intense space-time curvature that routes, durations, escape possibilities, and signal behaviour all become extreme. Time slows severely relative to distant observers. Light paths bend inward. There is a boundary beyond which return is no longer possible. None of this can be captured by saying space is bent while time sits outside the event taking notes. The whole structure is involved, and the closer one gets to these extremes, the more obvious the inseparability becomes. Even far from black holes, though, the same principle holds. Think about standing on Earth versus floating far away from any major mass. On Earth, your clock runs at a different rate than it would in deeper emptiness. Your path through space-time is different. Light climbing upward from the Earth changes frequency. Falling bodies follow paths determined by Earth's mass. All of these are connected effects. They are not a list of unrelated inconveniences caused by gravity meddling in multiple departments. They are the unified signs of one geometry being altered. There is a temptation to ask whether, at least conceptually, one could imagine a theory where only space bends and time remains absolute, provided one worked hard enough. In a purely imaginative sense, one can imagine many things. One can imagine a universe where spoons sing and tax forms complete themselves. The question is whether such a theory describes our world consistently. For our universe, the answer appears to be no. A theory with curved space but rigid universal time cannot reproduce the full package of relativistic gravitational effects with the elegance and consistency that general relativity achieves. It misses the behavior of clocks, misrepresents the role of light, and fractures the very union that special relativity had already established. This matters because special relativity had already killed universal time before gravity entered. Once Einstein had shown that motion changes the measurement of duration and that simultaneity is relative, gravity could not simply arrive later and start curving space while restoring old-fashioned time behind the scenes. The damage, if one wishes to call it that, had already been done. Time was already part of the geometric structure. General relativity then extended that structure by making it dynamic. It would make little sense to sew space and time together in one theory, and then pretend gravity can pinch only the spatial threads without disturbing the temporal ones. Another helpful way to think about it is through the experience of observers. In relativity, each observer has their own clock and their own path through space-time. Gravity affects both the path and the ticking of the clock. If only space were bent, observers at rest in different gravitational environments would still share one universal time, but they do not. Put identical clocks at different altitudes, and they part ways. That simple fact is enough to end the argument. Nature has already answered the question experimentally. Gravity changes durations. Therefore, time participates in the curvature. What about ordinary intuition? It still resists. We do not wake up feeling our personal timeline has been distorted by the stairs we climbed. We do not notice that time is different at the top of a mountain than at sea level. We do not sense the geometry of space-time when we drop our keys, though we may sense many other things. But ordinary intuition is not the measure of what is fundamental. It is an adaptation to a narrow range of conditions. The effects are small at human scales, so the old separation survives in daily thought. Science steps in precisely because daily thought is not enough when the goal is accurate description. There is something unexpectedly satisfying in how all this hangs together. The same theory that explains why planets orbit, why clocks differ with gravity, why light bends near the sun, why satellites need timing corrections, and why extreme objects warp the world so severely does so by refusing to split space from time. It is not juggling separate fixes, it is applying one idea consistently. That is often the mark of a deep theory. It makes many strange things look like different faces of the same underlying structure. One can even say that gravity is what makes the inseparability of space and time impossible to ignore. In special relativity, the union is already there, but much of daily life can still trick you into treating it as a technical point relevant mostly to fast motion. Gravity brings the lesson home. It reaches into the behavior of clocks at rest relative to one another. It alters the meaning of staying put. It tells you that even simply standing on the ground is not a neutral condition. Once mass is present, the full geometry becomes active, and any hope of isolating space from time starts to look like nostalgia rather than physics. This is also why phrases like the flow of time can become misleading near strong gravity. Time does not flow universally through a gravitational field, as though it were poured over a shaped landscape. Its rate is part of the landscape. The temporal dimension is structured differently from place to place. That is not metaphor, it is what clocks report. And because clocks are physical objects, their report is part of the world, not commentary on it. So when we say you cannot bend space without bending time, the statement is not a dramatic flourish meant to make relativity sound mysterious. It is a concise summary of what general relativity actually requires. Gravity shapes the full space-time metric. It changes how distances are measured, how durations are measured, how light travels, how causality is arranged, and how free bodies move. To try to keep time untouched while space bends is to pull apart a theory whose power comes from its unity. And once that unity is taken seriously, there is a place in the universe where the consequences become so severe that even our best ordinary language starts to fail a little. There are regions where curvature becomes immense, escape becomes impossible, and the distinction between what the world looks like from far away and what it feels like up close becomes almost unbearable in its strangeness. That is where the next step waits, because once space-time is allowed to bend together, black holes become less like science fiction props and more like the most uncompromising objects the theory has to offer. If general relativity is the theory that finally forced us to stop thinking of space and time as separate furnishings, then black holes are the place where that lesson becomes impossible to ignore. They are not merely strange objects sitting somewhere out in the universe behaving badly for dramatic effect. They are what happens when gravity tightens its grip on space-time so severely that the usual comforts of everyday intuition begin to fail one by one. Distance stops behaving in the familiar way. Time stops behaving in the familiar way. Light itself, which so often acts as the final referee in these matters, loses its usual freedom to escape. And all of this happens not because physics has broken down in a casual sense, but because physics is showing us just how far the structure of space-time can be pushed. It helps to begin with what a black hole is not. It is not a giant cosmic vacuum cleaner roaming the galaxy, greedily swallowing everything in sight with theatrical enthusiasm. That image is popular because it is vivid, but it is misleading. If the sun were somehow replaced by a black hole of the same mass, the Earth would not instantly be hoovered into oblivion. It would continue orbiting much as before, though admittedly under lighting conditions that would make gardening feel a bit more challenging. A black hole exerts gravity according to its mass, just like any other object. What makes it extraordinary is not that it pulls from farther away than ordinary matter. What makes it extraordinary is how much mass is compressed into how little space, and what that does to the surrounding space-time. A black hole forms when enough mass is squeezed into a sufficiently small region that escape becomes impossible once you cross a certain boundary. That boundary is called the event horizon. It is one of the most important ideas in all of modern physics, because it is not a solid surface in the normal sense. You cannot park a chair on it, or paint it a tasteful shade of blue. It is a limit in space-time, a point of no return. Outside it, light can still in principle escape to the wider universe. Inside it, all future directed paths lead inward. That last phrase matters. A black hole does not trap light by grabbing it with claws. It traps light because the geometry of space-time has become so distorted that every route forward points deeper in. This is where the old language of force begins to feel badly underdressed for the occasion. If gravity were simply a pulling influence across ordinary space, one might imagine light trying very hard and failing to climb out, like a runner on a steep hill. But general relativity says something more severe. Near and beyond the event horizon, the structure of space-time is arranged in such a way that escaping outward is no longer part of the available future. It is not merely difficult, it is geometrically forbidden. In that sense, a black hole is less like a pit, and more like a region where the directions available to causality itself have been rearranged. This makes black holes a perfect demonstration of why space and time cannot be separated. If you try to describe them using curved space alone, you would miss the central fact that time itself is part of what has gone strange. Clocks near a black hole do not behave as clocks far away do. To a distant observer, processes near the horizon appear slowed dramatically. Someone falling inward seems to approach the horizon more and more slowly, their signals becoming weaker and redder, their clock appearing to take longer and longer to tick. From far away, it can look as though time is dragging to a near standstill at the edge. Yet for the falling observer, matters are different. If the black hole is large enough and the tidal forces at the horizon are not yet severe, they cross the event horizon in finite proper time without witnessing some great cosmic pause button being pressed. Their own clock continues, their own experience moves forward. This difference between the outside view and the infalling view is one of the reasons black holes are so unsettling. They force us to confront just how much the measurement of time depends on the observer's path through space-time. There is no universal clock standing above the scene, announcing one official version. That alone would make black holes important. But they go further. They reveal a point at which our best understanding of space-time reaches its limit. According to classical general relativity, if matter collapses beyond a certain point and nothing halts the collapse, it continues inward until it reaches what is called a singularity. The word is dramatic, but the underlying meaning is simple enough. It marks a place where the theory predicts that curvature becomes unbounded, and the usual description of space-time ceases to function in the way we understand it. In practical terms, it means general relativity has been pushed to a breaking point. It is very important to be careful here. Physicists do not speak of a singularity because they believe the universe enjoys placing infinities into nature like decorative ornaments. A singularity is better understood as a sign that the theory has gone beyond the range where it can be expected to give a complete account. It is the mathematical equivalent of a map that works brilliantly across an entire country, and then, at one particular edge, develops a large and deeply unhelpful tier. The existence of that tier does not mean the country stops, it means the map is incomplete. Black holes are therefore not just exotic objects, they are stress tests for our understanding of reality. They tell us how far general relativity can go, and where something deeper is likely required. This is one reason they sit at the centre of so many efforts to unite gravity with quantum theory. General relativity describes the large-scale geometry of space-time with astonishing success. Quantum mechanics describes the microscopic world with equally astonishing success. But near the singular core of a black hole, where matter is compressed enormously and curvature becomes extreme, those two great frameworks are expected to collide conceptually. And right now, they do not get along as smoothly as one might like. Still, even without solving that deeper problem, black holes teach us a tremendous amount about space-time. Consider the event horizon again. It is not a material shell. If you fall through it, assuming the black hole is sufficiently massive, you do not necessarily collide with anything special right at that boundary. Locally, your immediate surroundings may seem unremarkable. That is part of what makes the horizon so strange. Its importance is global, not local. It divides regions of space-time according to what futures are possible. Outside, escape remains possible. Inside, it does not. The horizon is a causal boundary. That phrase can sound technical, but it points to something profound. A black hole is not defined only by what matter it contains. It is defined by what information can and cannot reach the outside world. Once you cross the horizon, the rest of the universe loses the ability to receive signals from you. You may continue existing for a time according to your own clock, but the wider cosmos no longer has access to your later story. In that sense, black holes are not only about matter and gravity, they're about communication, causality, and the limits of what space-time allows events to tell one another. This becomes especially interesting when one remembers that light normally defines the basic causal structure of relativity. Light tells us what signals can travel where. It sets the speed limit and determines how events can influence one another. Near a black hole, even that structure gets bent inward. Light cones, to use the geometrical language, tip so severely that future directed paths lead toward the centre. Again, the key point is that this is not merely a story about strong gravity acting on objects in space. It is a story about the geometry of space-time itself being arranged so that inward motion is written into the structure of the future. If that sounds severe, it is because it is. A black hole is the clearest known example of space-time becoming so curved that the usual distinction between going inward as a spatial direction and going forward as a temporal direction begins to blur in disturbing ways. Outside the horizon, one can still imagine choosing whether to move toward or away from the black hole. Inside, moving inward becomes as unavoidable as moving toward tomorrow. That is why one cannot think of black holes properly without treating time as part of the geometry. The inner region is not just a place you happen to be in, it is a fate built into the structure of space-time. One of the more famous consequences of this comes from the strange way distant observers perceive in falling matter. Suppose a spacecraft approaches a black hole while sending out regular pulses of light. To the people on board, their clocks tick normally, they continue inward. But to someone far away, the pulses arrive more and more slowly, stretched by the gravitational field. The spacecraft appears to dim and freeze near the horizon, never quite crossing it within the distant observer's own coordinate description. This can sound like a contradiction, but it is not. It is another reminder that time is not universal. Different observers organize the story differently because their relationships to the space-time geometry are different. The physical consequences of strong curvature do not end with timing. Black holes also subject objects to tidal forces, the result of gravity changing significantly over relatively short distances. If you fell feet first toward a small black hole, the pull on your feet would be much stronger than the pull on your head, stretching you out. Meanwhile, the sides of your body would be compressed inward. The effect has acquired an unfortunate nickname involving pasta, which, while memorable, does rather undersell the seriousness of the experience. In larger black holes, the horizon can be crossed before these forces become catastrophic, but deeper in they eventually become overwhelming. Again, what matters is that the severity comes not from some hidden monster inside the hole, but from how space-time curvature varies from place to place. Black holes also forced physicists to think hard about thermodynamics and information. For a long time, they seemed like perfect prisons. Matter falls in, the horizon hides the details, and the outside world is left only with broad information such as the black hole's mass, charge, and spin. This simplicity was elegant but troubling. Then Stephen Hawking showed that quantum effects near the horizon imply black holes are not perfectly black after all. They can emit radiation and gradually lose mass. That result changed everything. Black holes became thermodynamic objects with temperatures and entropies. They were no longer silent endpoints only. They became participants in a deeper puzzle. The trouble is that if black holes can evaporate over vast stretches of time, what happens to the information about what fell in? Quantum theory does not like information being truly destroyed. General relativity, taken naively, seems to allow horizons that hide it completely and singular endings that offer no easy route back. This tension produced the black hole information problem, one of the most important unresolved issues in theoretical physics. It is not merely a bookkeeping question. It touches on what reality permits, how space-time and quantum mechanics fit together, and whether our current understanding of black holes is conceptually complete. This is why black holes are often called laboratories for fundamental physics, even though one would need a rather unusual health and safety policy to treat them as ordinary research venues. They sit at the edge of what we know. They are astrophysical objects, yes, observed in the universe through their effects on nearby matter, through gravitational waves from mergers, and now even through direct imaging of the shadow regions around them. But they are also theoretical crossroads. They bring together gravity, spacetime, thermodynamics, quantum theory, and information in a way few other objects can match. The first direct image of a black hole's shadow region was especially striking not because it showed us some neat circular hole punched in the cosmos, but because it turned years of theory into something visible. The glowing ring and dark central region matched what one expects when light from hot matter is bent and trapped by extreme gravity near an event horizon. It was a portrait not of a solid object in the ordinary sense, but of space-time distorted so profoundly that the paths of light themselves sculpt what we see. Once again, the object is not meaningful if treated merely as a chunk of matter sitting in space. Its identity is inseparable from the geometry around it. There is also a cosmic modesty lesson here. Human beings spent centuries learning that Earth is not the centre of the universe, that the sun is one star among many, that galaxies fill the cosmos, and that much of reality is stranger than our daily habits suggest. Black holes continue that tradition. They remind us that the universe contains regions where our familiar categories are not wrong so much as incomplete. Near these objects, asking what time is doing without asking what space is doing becomes impossible. Asking what path something follows without asking how clocks behave becomes impossible. Everything is linked. At the same time, black holes are not exceptions to the union of space and time. They are its most demanding expression. They do not introduce a new principle so much as reveal the existing principle under extreme conditions. Gravity has always shaped space-time together. Light has always marked the causal structure. Motion has always depended on geometry. Black holes simply take these truths and turn the volume up until even intuition, which is usually quite stubborn, can no longer pretend not to hear them. And that is why they mark a kind of breaking point of the cosmos. Not because the universe falls apart there in a melodramatic sense, but because our present theories reach their sharpest test. General relativity predicts their existence and describes much about them magnificently. Quantum theory insists on questions that relativity alone cannot fully settle. The result is a place where modern physics meets its own limits with unusual honesty. We know enough to describe the horizon, the curvature, the time dilation, the mergers, the shadows, and the radiation. We do not yet know enough to say we have finished the story. That unfinished quality matters, because black holes are not the only places where space-time refuses to sit still. The cosmos as a whole is not static either. Space is not merely curved around massive bodies. On the larger scales, it expands, galaxies recede, distances grow, and once again, time is part of that process as well, because an expanding universe is not just a larger room with the same old clock on the wall. It is another case where the geometry of space-time itself is doing the real work. If black holes show us what happens when gravity grips space-time with overwhelming local intensity, the expanding universe shows us the same union on the largest scale imaginable. Instead of one region becoming so curved that escape turns into a problem, the cosmos as a whole reveals that the structure of reality is not sitting still in the background, while galaxies politely move around inside it. The background itself evolves. Distances between faraway galaxies change because space is not a fixed container, and because space and time are joined, that expansion is not just a story about where things are. It is also a story about how the history of the universe unfolds. The cosmos does not merely contain events, it has a changing space-time structure that shapes what those events can be. For a very long time, many people assumed the universe on large scales was static. That assumption was not ridiculous. It matched what the sky seems to suggest when viewed without modern instruments. The stars appear fixed in broad patterns. The heavens look steady, almost timeless in their arrangement, especially compared with the bustle and breakdowns of life on Earth. Even after Newton and Einstein, there remained a natural human desire to imagine the universe as a kind of permanent stage, perhaps populated by moving actors, but fundamentally stable in its overall form. It took a surprisingly long time for people to accept that the stage itself might be changing shape. Einstein himself, after developing general relativity, first leaned toward a static universe. His equations, left to their own devices, suggested that space-time on the larger scales should not simply hold still. Matter and energy would influence the cosmic geometry, and the result was naturally dynamic. Yet Einstein preferred a universe that was stable overall, so he introduced an extra term into the theory in order to hold the cosmic structure in balance. In effect, he adjusted the mathematics to keep the universe from expanding or collapsing. This was understandable. At the time, there was no clear observational evidence that the cosmos as a whole was changing size. A static universe felt sensible. It felt dignified. One imagines it appealed to the part of the human mind that likes old buildings, consistent weather, and clocks that do not need resetting. But the universe was not particularly interested in remaining sensible for our convenience. Observations by astronomers, especially Edwin Hubble and others working in the early 20th century, showed that distant galaxies are moving away from us, and that the farther away they are, the faster they appear to recede. This was not because Earth happened to sit at the centre of some cosmic fireworks display. The natural interpretation was far more remarkable. Space itself is expanding. Galaxies are not merely flying through a pre-existing void like sparks through the air. The distances between large-scale structures are increasing because the space-time geometry of the universe is changing. That distinction matters enormously. If galaxies were simply moving through fixed space, one might imagine the universe as a grand traffic pattern. Some galaxies head this way, some that way, and we happen to see many going outward. But cosmic expansion is subtler than that. It is not primarily motion through space. It is the growth of space between distant objects. The usual analogy is that of raisins in rising bread dough. As the dough expands, each raisin sees the others moving away, not because the raisins are propelling themselves through the dough in some grand panic, but because the dough itself is stretching. It is not a perfect analogy, but it helps. No one raisin occupies the special centre of expansion, and the increasing separation is a property of the medium, not just the objects within it. Now, one must be careful with such analogies because bread dough does not come with relativity, galaxies, or philosophical consequences about time. Still, the key lesson survives. If space expands, then our older instinct to picture the universe as a fixed room becomes unreliable. And because space and time belong together, the expansion of space is bound up with the temporal history of the universe. You cannot speak meaningfully about an expanding cosmos without speaking about cosmic time, because the amount of expansion depends on when in the universe's history you ask the question. This is where the title of this section becomes especially important. The expanding universe is not just about stretching space. It is about the stretching of time itself in a very particular sense. To see why, we need to look at light again, because light continues to serve as our most faithful witness to the structure of space-time. When light travels across an expanding universe, it does not simply cross fixed distances while the cosmos keeps the same temporal rhythm underneath. As space expands, the light itself is stretched. Its wavelength grows longer. This is what we call cosmological redshift. The light arriving from distant galaxies is shifted toward the red end of the spectrum, not simply because the galaxies are moving away in the ordinary everyday sense, but because the space through which the light travelled has expanded while the light was on its way. That means the universe leaves a record of its own expansion in the light it sends us. A distant galaxy is not just far away in space, it is far away in time. The light we receive tonight may have begun its journey billions of years ago. When we look deep into the cosmos, we're not looking across a static arrangement. We're looking back into earlier stages of cosmic history. Distance becomes inseparable from time in a way that is almost literal. Farther means older, because light takes time to travel and because the universe itself changes while the light is en route. This already tells us that the expansion of the universe is a space-time phenomenon rather than a purely spatial one. A more expanded universe is not simply a larger version of the same place with the same temporal structure. It is a later state in the cosmic history of space-time. The geometry changes over time, and that changing geometry affects how light propagates, how galaxies separate, how matter clumps together, and how the universe cools. Time is not a spectator here. It is one of the coordinates through which the expansion is defined. One of the most striking pieces of evidence for this is the cosmic microwave background, the faint afterglow left over from the early universe. This radiation comes from a time when the cosmos was far hotter and denser than it is now, long before stars and galaxies had settled into the forms we know today. At that early stage, matter and light were coupled in a hot plasma. Eventually the universe expanded and cooled enough for atoms to form and for light to travel freely. That light has been crossing the universe ever since, and because space has stretched during its journey, the light has been stretched too, all the way down into the microwave range. What we observe in that background is therefore not just ancient light. It is ancient light altered by the expanding space-time through which it travelled. The universe has cooled because it has expanded. The wavelengths have grown because space has grown. If time was separable in the old absolute sense, one might imagine expansion as merely a change in size, occurring against a perfectly rigid temporal backdrop. But the actual physics tells a richer story. The age of the universe, the size of the universe, the temperature of the background radiation, and the distribution of matter are all linked features of an evolving space-time history. This also changes what we mean by the age of the universe. In ordinary life, age feels personal. A person is this many years old. A building is that many years old. A tree stands somewhere between quietly ancient and in need of better soil. But the age of the universe is not the age of something sitting within time while time itself remains untouched. It is the measure of how much cosmic time has elapsed along the large-scale history of expanding space-time. It refers to the universe's development from an earlier hot dense state to its current more dilute one. In other words, the age of the universe is already a statement about space-time evolution, not merely a number attached to a static object. The more one thinks about this, the stranger it becomes. In the old picture, you might ask what the universe is expanding into, as though it were a balloon growing inside a room, but that question smuggles in the wrong image. The expansion of the universe does not require a larger surrounding space for the cosmos to spread into. It is space itself that is expanding. There need not be an external container at all. This is another moment where daily intuition, trained on objects inside rooms and liquids inside jars, begins to struggle. We want an outside because that is how ordinary things grow. But the universe is not growing like bread in an oven. The geometry itself is changing, and once again, time is part of the explanation. The universe at one cosmic time had a different scale than it does at another cosmic time. Galaxies that are now far apart were once much closer together. Temperatures were higher, densities were greater, light had different wavelengths. All of these statements are temporal as well as spatial. They describe not just the arrangement of things, but the history of the arrangement. An expanding universe is inseparable from the passage of cosmic time because expansion is what the geometry is doing as time advances. There is also a subtle but important sense in which expansion stretches time observationally. Suppose a distant exploding star brightens and fades over a certain duration in its own local environment. If the universe has expanded significantly while its light travelled to us, then we do not simply receive redder light. We also receive its whole pattern of change stretched in time. Events in very distant galaxies can appear to unfold more slowly from our point of view, because the expansion of the universe stretches the arrival times of the signals as well. In that sense, cosmic expansion does not only alter the colour of light, it alters the observed timing of distant processes. This effect is one of the clearest signs that time itself is implicated in the large-scale evolution of the universe. It is not that clocks everywhere in the universe are arbitrarily misbehaving. It is that signals crossing an expanding space-time arrive in ways that reflect that expansion. The distant universe is not only spatially far away, it is temporally stretched in the information it sends us. A supernova billions of light years away does not merely look dimmer and redder. Its rise and fall can appear slowed by the expansion of space-time between there and here. That is a remarkable thing to realise. The universe is not just a gallery of remote objects, it is a historical archive in which space and time are mixed together. When we observe distant galaxies, we are watching earlier stages of cosmic development through light that has been shaped by the intervening expansion. Astronomy becomes a form of time travel in the mild but genuine sense that looking far away means looking back. This also means that the universe had a beginning of a very special kind, or at least a beginning to its current expanding history as described by our best large-scale models. It did not begin as an explosion into pre-existing emptiness in the ordinary way people often imagine. It began as a hot, dense state from which space-time itself evolved. The so-called Big Bang is easily misunderstood because the word bang encourages images of fireworks, shrapnel, and a deeply regrettable party trick. But the cosmological meaning is different. It marks an early state of the universe when matter, radiation, space, and time were all compressed into conditions unlike anything we encounter now. The important point is that this was not simply matter exploding into space while time waited with a clipboard. The whole space-time system was involved from the start. As one goes back earlier and earlier in the universe's history, densities rise, temperatures rise, and our familiar descriptions become harder to push all the way to the beginning. Once again, our theories approach a limit. General relativity describes the large-scale expansion magnificently, but at the earliest moments, quantum effects are expected to matter greatly. Just as black holes drive us toward the need for a deeper theory, the early universe does the same. The cosmos seems to present us with two great frontiers where space-time is pushed to extremes. One is the interior collapse of black holes, the other is the earliest history of expansion. At both ends, the union of space and time remains essential, but our present understanding is not yet complete. In the meantime, the expanding universe gives us another profound lesson. Space is not just a static geometry, and time is not just a universal flow. The large-scale cosmos evolves. Galaxies form because matter clumps over time within that evolving geometry. Structures emerge because the universe cools and expands. Stars burn, galaxies collide, heavy elements are forged, planets form, and life becomes possible not in spite of cosmic history but because of it. A perfectly static universe would be a very different place, and likely not a place in which this kind of complexity would arise at all. There is something deeply human about this realization, though human beings are not always quick to notice it. We often imagine permanence as comforting. A changing universe can sound unsettling at first, as though the house itself has started shifting around us. But the evolving cosmos is also what makes history, structure, and development possible. The stars that made the heavier elements in your body did so in an unfolding universe. The galaxies that arrange themselves into the vast patterns we observe did so over time. The very possibility of asking questions about space and time depends on beings who emerged within a cosmos that has not been static for a single moment. Modern observations have made this story even stranger. The expansion of the universe is not merely continuing, it appears to be accelerating. Distant galaxies are receding in a way that suggests some form of cosmic repulsion, or dark energy is influencing the large-scale behaviour of space-time. The exact nature of this remains one of the great open questions in cosmology. Is it a property of empty space itself? Is it a field of some kind? Is it a sign that our understanding of gravity is incomplete on the larger scales? We do not yet know. But whatever the answer, it further proves the main point. Cosmic history is written into space-time itself. The universe is not a fixed arena with a few moving decorations. Its very geometry evolves. That also reshapes our sense of the future. If expansion continues forever, galaxies beyond our local region may eventually recede beyond the point where their light can ever reach us. The night sky of the far future could be a lonelier place, with distant structures fading beyond view as space-time carries them away from causal contact. If that sounds slightly melancholy, that is because cosmology occasionally has a flair for delivering existential news with very little warning. Yet even here the lesson is not just emotional, it is physical. The future visibility of the cosmos depends on the evolution of space-time. Time and cosmic geometry remain locked together. So when we speak of the expanding universe and the stretching of time itself, we're not indulging in metaphor. We're describing a real physical relationship. Light is stretched by expansion. The observed duration of distant events is stretched by expansion. The scale of the universe changes with cosmic time. The thermal history of the universe changes with cosmic time. Distance and age become intertwined in observation. The whole story only makes sense because space and time belong to one evolving framework. And all of this leads naturally to a deeper question. If space-time can expand on the larger scales and curve violently around black holes, what happens when we descend to the smaller scales, where quantum theory rules with all its usual confidence and complication? Because the next challenge is not whether space and time are joined. That much is already clear. The challenge is whether the very thing we call space-time remains smooth and continuous all the way down, or whether at the deepest level reality becomes stranger still. By the time we reach the quantum world, the story becomes difficult in a new way. Up to this point, relativity has already asked us to let go of several comforting habits. We have had to give up absolute time, accept that motion changes duration and distance, allow gravity to shape the geometry of space and time together, and admit that black holes and cosmic expansion push this joined structure into regimes that common sense would never have invented on its own. That is already quite a lot to ask of the human brain, especially one that is usually occupied with breakfast, unpaid bills, and whether it really locked the front door. But quantum theory arrives with its own demands, and rather than quietly fitting into the relativistic picture, it starts asking whether space-time itself is as smooth and straightforward as we have been pretending. This is the point where many people are tempted to imagine that quantum mechanics is simply the science of very tiny particles doing strange and inconvenient things. Electrons behave oddly. Atoms refuse to act like miniature solar systems. Particles seem to come with probabilities instead of neat little trajectories. All true enough as far as it goes. But the deeper issue is that quantum theory changes how we think about physical reality at the most basic level. And once you start applying that way of thinking to the universe itself, especially to gravity and space-time, the ground beneath your concepts begins to wobble. In ordinary quantum mechanics, time is treated rather differently from space. This is already suspicious. In relativity, space and time are joined into space-time. In standard quantum theory, however, time often enters the equations as an external background parameter. It is the thing with respect to which systems evolve. Space, meanwhile, is where probability distribution spread and where measurements are discussed. The result is an odd mismatch. The theory that describes the very small tends to act as though time is still sitting outside the system with a stopwatch, while the theory that describes gravity says time is part of the dynamical structure of reality itself. These two ways of thinking coexist with astonishing practical success in their own domains, but they do not sit together comfortably. This discomfort becomes impossible to ignore when we ask what happens in situations where both quantum effects and gravity should matter strongly. The early universe is one such case. The deep interior of black holes is another. In those places, the smooth classical space-time of general relativity is expected to meet the jittery, probabilistic, uncertainty-filled world of quantum mechanics. And when the meeting begins, it quickly becomes clear that we do not yet have a complete script for what follows. One reason the problem is so difficult is that quantum theory does not merely add fuzziness to an otherwise tidy picture. It changes what measurement means. In everyday life, we imagine that the world has definite properties, and measurement simply reveals them. A chair is here, a clock reads this, a particle is somewhere, even if we have not checked yet. Quantum theory complicates that. It tells us that some properties are not simultaneously well defined in the way classical intuition expects. Systems are described by states that encode possibilities, and measurement does not behave like the quiet act of reading off a pre-written answer from nature's notebook. It plays a more active role. That is strange enough when we're talking about electrons or photons. It becomes much stranger when the thing under discussion is spacetime itself. What would it mean for spacetime to be in a quantum state? What would it mean for geometry to be uncertain? Can space be in a superposition? Can time? These questions are not decorative philosophy. They sit at the centre of the effort to build a quantum theory of gravity. To understand why, it helps to remember what general relativity says. Gravity is not a force moving through a fixed arena. Gravity is the geometry of space-time changing in response to mass and energy. So if quantum theory is supposed to apply universally, then the geometry itself should be subject to quantum principles. It should not remain the one sacred classical backdrop while everything else becomes probabilistic. But once you say that, you run into a problem that is as conceptually awkward as it is important. If space-time itself is fluctuating quantum mechanically, what becomes of the very stage on which ordinary quantum mechanics describes things evolving in time? This is sometimes called the problem of time, and the name is so modest that it almost feels unfair. It sounds like something you might blame on a late train or a badly designed kitchen timer. In theoretical physics, however, it refers to a genuine conceptual collision. In general relativity, time is part of the geometry and depends on the observer and the gravitational field. In ordinary quantum theory, time is treated more like a fixed external parameter. Try to merge the two, and the role of time becomes unclear. If the whole universe is being described quantum mechanically, there is no obvious external clock standing outside it to keep score. Yet without time, our usual language of evolution becomes very difficult to formulate. This is one reason some approaches to quantum gravity suggest that time may not be fundamental in the way we usually imagine. That idea sounds dramatic, and it is, but it should be approached carefully. Saying time may not be fundamental does not mean clocks are fake or that Tuesday never happened. It means that at the deepest level of description, the world may not be built out of a smooth flowing temporal dimension in the way classical physics suggests. Time might emerge from more basic relationships, much as temperature emerges from the collective behaviour of molecules rather than existing as an ingredient inside a single atom. That possibility has attracted serious thinkers because it offers one way to make sense of the clash between relativity and quantum mechanics. If space-time is not fundamental but emergent, then perhaps the smooth geometry of general relativity appears only at large scales, while something more primitive lies underneath. Just as a car motion surface can emerge from countless molecular interactions, continuous space-time might emerge from deeper quantum structures. At human scales and even astronomical scales, the geometry looks smooth and dependable. But at the smallest scales, perhaps it becomes grainy, relational, or built from ingredients that do not themselves look like space and time in the familiar sense. This leads us to the idea of the Planck scale, the regime of extraordinarily tiny distances and brief durations where quantum gravity is expected to matter. At such scales, many physicists suspect the ordinary smoothness of space-time may break down. One often hears phrases like quantum foam used to describe this possibility. The image is informal but suggestive. Instead of a serene geometric backdrop, space-time at the smaller scales may be restless, fluctuating, and structurally uncertain. Tiny regions may not have the clean classical properties we assign to larger ones. Distances and durations themselves may become subject to quantum indeterminacy. Now, one should be careful not to picture the Planck scale as though it was simply ordinary space chopped into very tiny cubes, like a badly made sugar substitute. The deeper issue is not just smallness, it is that the concepts of here and now may lose the clean meaning they have in larger scale physics. If geometry is quantum, then asking for a perfectly precise location or interval may no longer make sense in the classical way. The world may still have structure, but it may not be the smooth, continuous structure our intuition prefers. Several approaches to quantum gravity try to say what that deeper structure might be. One family of ideas suggests that space-time is woven from discrete units or networks, not unlike a fabric whose threads become visible only when examined with impossible closeness. Another suggests that the fundamental objects are not point particles, but extended entities whose different vibrational modes give rise to the variety of particles, and perhaps to gravity itself. Yet another line of thought leans heavily on information, entanglement, and relationships, proposing that space-time geometry may emerge from patterns of quantum connection rather than from pre-existing spatial substance. These ideas differ sharply in method and detail, and it would be dishonest to pretend there is already one settled answer. There is not. This is one of the most active and uncertain frontiers in theoretical physics. But the common theme is revealing. In one way or another, many attempts to reconcile quantum mechanics with gravity lead to the suspicion that space-time is not the final layer of reality. It may be something that appears when a deeper structure is viewed at the right scale, in the same way that a smooth melody appears when many individual notes are arranged in time. Entanglement has become especially important in this discussion. In quantum theory, entangled systems are linked in such a way that their combined state cannot be fully reduced to independent descriptions of each part. The systems are correlated more deeply than classical thinking would allow. What has made this idea so interesting in recent years is the growing suggestion that space-time geometry itself may be connected to patterns of entanglement. In some theoretical frameworks, the degree of entanglement between regions seems to track features of spatial connectivity. In loose terms, it begins to look as though quantum connectedness may help build geometric connectedness. That is a remarkable reversal. Space once seemed like the unquestioned background in which relationships happened. Now there are hints that relationships may help generate what we call space. If that is true, then time may also need to be reconsidered in similar terms. Perhaps the flow we experience is not a primitive river, but a large-scale feature emerging from changes in quantum correlations, information flow, or ordered sequences of state changes. That does not make time unreal in the everyday sense. It makes it more like weather. Real, measurable, consequential, but not fundamental in the same way as the microscopic processes that underlie it. Black holes again play a starring role in these debates because they sit right where quantum theory and gravity must both be taken seriously. The information problem in particular has pushed physicists to rethink what space-time horizons mean. If information cannot be destroyed, then the story of matter falling into a black hole and disappearing behind an event horizon cannot be the whole story in the naive classical sense. Something about quantum theory, space-time geometry, or both must revise the picture. In trying to resolve this, people have discovered deep links between gravity, entropy, quantum entanglement, and the geometry of horizons. Black holes have become less like cosmic oddities and more like pressure points, where hidden principles of reality are forced into view. There is a further complication. In quantum field theory, which successfully combines quantum mechanics with special relativity for non-gravitational phenomena, particles are treated as excitations of fields that live on a space-time background. This framework has been spectacularly successful. It underlies much of modern particle physics. But once gravity is brought in fully, the background itself should no longer be fixed. This means one of our best tools is, in a sense, built on a scaffold that gravity asks us to remove. It is as though we have become brilliant at staging performances in a theatre, only to discover that the theatre itself is a living organism and the walls are not guaranteed to stay in place. That is why quantum gravity is not simply one more technical challenge to be solved with enough determination and stronger coffee. It asks what physical description looks like when the background of all description becomes part of the quantum system. It asks how to define locality when geometry may fluctuate. It asks how to speak of change when time itself may be emergent. It asks whether causality, distance, and duration survive in recognizable form at the deepest level? These are not the sorts of questions that allow for casual optimism, and yet there has been progress, even if it is not yet final. We have learned that black holes have entropy. We have learned that horizons radiate quantum mechanically. We have learned that geometry and information seem to be linked in surprising ways. We have learned that many classical features of spacetime may be recoverable as large-scale limits of deeper structures. And perhaps most importantly, we have learned that the union of space and time is not weakened by the quantum problem. If anything, it becomes more essential. The mystery is no longer whether space and time belong together. The mystery is what kind of thing their union actually is at the most fundamental level. There is also a more philosophical consequence to all this, though it remains grounded in physics. Human beings are accustomed to thinking in terms of locations and moments. We live by maps and calendars, addresses and schedules, where and when. Those categories are not arbitrary. They are magnificently useful. But at the edge of space-time, quantum theory suggests that these categories may not be primary. They may be the large-scale language of creatures like us, embedded in a certain regime of reality, rather than the universe's first language. That does not make them false. It means they may be translated from something deeper. The comparison to temperature is helpful here, though only up to a point. Temperature is real. It affects matter, engines, weather, biology, and comfort levels in badly heated rooms. But it is not a basic ingredient carried by individual atoms in isolation. It emerges from collective behaviour. If space-time is like that, then asking what time fundamentally is may be a bit like asking whether wetness is hiding inside a single water molecule. The answer is not that wetness is an illusion. It is that wetness belongs to a larger level of organisation. Some physicists suspect space and time may be similar. Of course, there are dangers in talking this way. One can easily slide into vague mysticism, which is very satisfying for about 30 seconds, and then leaves everyone worse informed than before. The responsible thing to say is that we do not yet know the final structure. We have mathematical programs, suggestive clues, partial successes, elegant ideas, and vigorous arguments. We have black hole puzzles, cosmological questions, and hints that geometry and information are entangled more deeply than anyone once imagined. But we do not yet possess the final, experimentally confirmed theory that tells us exactly what spacetime becomes in the quantum regime. That uncertainty, however, is not a failure. It is a sign we have reached a real frontier. Physics is not a museum of settled facts. It is a changing attempt to describe the world with increasing honesty. At the edge of space-time, honesty requires admitting that our best frameworks are incomplete when pushed together hard enough. General relativity gives us curved space-time, black holes, gravitational waves, and cosmic expansion. Quantum theory gives us uncertainty, entanglement, field excitations, and the microscopic structure of matter. Both are astonishing. Neither can simply dismiss the other. Where they meet, reality asks harder questions. And those questions circle back to the title we began with. Why can space and time not exist without each other? Quantum gravity does not weaken that question. It intensifies it. Even when space-time itself becomes suspect as a fundamental concept, what emerges from the deepest theories still seems unlikely to separate neatly into an independent where and an independent when. The old division remains gone. Whether space-time is smooth or granular, fundamental or emergent, classical or quantum corrected, the physical world resists being described by space alone or time alone. What survives is relation, structure, connectivity, history. That last word matters. History is built into the universe at every scale we understand. A particle interaction has an order. A star forms and dies. A galaxy evolves. Light carries records from the early cosmos. Black holes trap and perhaps transform information. Even if time is emergent, emergence itself comes with sequence and change. The physical world is not a pile of disconnected snapshots with no organizing relation. Something like temporality, whether fundamental or derived, remains essential to explanation, and something like spatiality, whether fundamental or derived, remains essential to structure. The mystery lies in how deeply these notions intertwine and from what deeper principles they arise. So the quantum edge of space-time does not leave us with a neat answer. It leaves us with a more interesting situation. The union of space and time appears secure in every successful large-scale theory we have, yet their ultimate status remains open. They may be woven from something beneath them. They may emerge from quantum information, discrete structures, or principles not yet fully understood. But whatever the final story turns out to be, it is increasingly hard to imagine a universe where one could keep the where while discarding the when, or keep the when while discarding the where, which brings us to the final step in this journey, where all these strands have to be drawn together and ask the simplest and hardest question of all. What would existence even mean if space and time did not arrive together? By now, the old separation has been worn down from almost every direction. Motion would not let it stand. Light would not let it stand. Gravity would not let it stand. Black holes certainly would not let it stand, and the expanding universe was no kinder. Even the quantum world, for all its unanswered questions, kept pushing us away from the idea that space and time could be treated as two independent facts that merely happened to cooperate. And so, we arrive at the final question in the clearest form possible. Why does existence need both space and time? The first answer is almost embarrassingly simple, because for anything physical to exist in a meaningful way, it must be possible to say not only that it is, but where it is and when it is. Remove either half, and the statement collapses into something incomplete. A physical event is not just an event, it is something happening somewhere and somewhen. A star exploding, a child being born, a leaf falling from a tree, a train arriving too late to be called punctual and too early to justify proper outrage. Every one of these is defined by both location and moment. Without place, there is no structure. Without time, there is no happening. That may sound almost too basic after everything we have covered, but basic things are often the ones most worth returning to. We do not usually notice how much work space and time are doing, because they are present in every ordinary sentence about the world. The cup is on the table, the meeting starts at 9, the storm reached the coast last night. The package is in the hall. Dinner was half an hour ago. A comet passed above the horizon before dawn. Physical life is described constantly through this partnership. We're so used to it that we treat it as grammar rather than revelation. Try removing space first. Imagine a universe with time but no spatial extension at all. No here and there, no distance, no direction, no larger and smaller in the ordinary physical sense. What would it even mean for multiple things to exist in such a world? How would they be distinct from one another? In our universe, distinction is not just a matter of naming, it is built into structure. This object is here, that one is over there, this star is far away, that one is nearer. Your hand is not the same as the lamp because they occupy different regions and have different boundaries. Even the structure of your own body depends on spatial arrangement. Heart here, lungs there, brain up above doing its best, bones and skin and blood arranged in relation to one another. Space is not an optional stage dressing. It is what allows structure, separation, and form. Without space, there is no meaningful way for a physical object to have shape. There is no distance for light to travel, no room for motion, no geometry for forces or fields, no inside or outside, no near or far, no path from one thing to another. You cannot build a planet, an atom, a person, or even a decent excuse for being late if there is nowhere for anything to be. A universe without space would not merely be cramped. Cramped still assumes dimension. It would be a universe in which physical distinction loses the meaning we rely on to describe any object at all. Now try removing time instead. Imagine a universe with spatial extension but no time, a frozen arrangement with no before and after. At first glance, that can sound easier to picture. Perhaps a kind of cosmic sculpture, all positions fixed in one eternal stillness. But the moment you ask what existence means inside such a world, the trouble begins. Without time, there is no change. Without change, there is no motion, no causation, no process, no development, no memory, no aging, no growing, no burning, no orbiting, no breathing, no speaking, no listening. A frozen universe may have arrangement, but it does not have events. It has no history, because history requires sequence. It has no action, because action requires one state giving way to another. And physical reality, as we encounter it and as physics describes it, is not just a collection of arrangements. It is a collection of processes. Stars shine because nuclear reactions proceed over time. Planets orbit because positions change over time. Organisms live because countless chemical and biological processes unfold over time. Conversation itself only exists because one word follows another. Music requires duration. A story requires sequence. Even a single heartbeat requires a before and after. Without time, the universe would not merely be quiet, it would be causally mute. This is why existence in the physical sense is not satisfied by shape alone or by sequence alone. It needs both structure and development. It needs things to be arranged, and it needs that arrangement to be capable of changing. Space gives the world form. Time gives the world unfolding. Space gives coexistence. Time gives succession. Space allows many things to be distinct at once. Time allows one thing to become something else. A world with one and not the other would not be a reduced version of our universe. It would be a radically different kind of reality. So different that much of what we mean by physical existence would no longer apply. There is another layer here, and it becomes clearer once we think not just about objects, but about relations. Physics is not only the study of isolated things, it is the study of how things relate. Distance is a relation. Duration is a relation. Velocity is a relation between distance and time. Causality is a relation between events ordered in time and connected through space. A field is a relation spread across space and evolving over time. Waves, particles, signals, collisions, decays, orbits, all of them rely on a framework in which both extension and succession matter. Remove one and the relations either collapse or become unrecognizable. Consider cause and effect, for instance. We rely on causality to make sense of reality at every scale. You let go of the cup and it falls. A star exhausts its fuel and changes state. A seed is watered and grows. A message is sent and later received. Cause and effect require time because causes precede effects, but they also require space because physical influence travels. The cup falls through space. Light crosses distance. Signals move from one place to another. Even in quantum theory, where causality becomes more subtle than ordinary intuition likes, the structure of influence still depends on the space-time relation between events. A cause with no temporal order is not a cause. A cause with no spatial context is not a physical cause in the familiar sense. Identity depends on both as well. It is easy to assume identity is simple. A thing is itself. Fair enough. But physical identity across time is more complicated than that. What makes you the same person you were yesterday? Your atoms have shifted around. Cells have died and been replaced. Thoughts have changed. Meals have happened. Mistakes have certainly happened. Yet there is continuity because your body and mind trace a connected history through space-time. You're not a single static object existing outside succession. You're an ongoing pattern. To speak of your identity requires space because your body has spatial organization, and time because that organization persists and changes in a connected sequence. A person is not just a shape. A person is a history. The same is true of everything from storms to galaxies. A hurricane is not merely a circular arrangement of air at one instant. It is a process that develops, moves, strengthens, weakens, and dissipates. A river is not just water occupying a shape, it is flow. A galaxy is not just a star pattern frozen in place, it evolves over billions of years. Even something that appears solid and ordinary, like a chair, exists within time through wear, temperature changes, chemical aging, and the quiet dignity of gradually becoming everyone's least favourite item to move house. Physical things endure by changing. Existence in our universe is not static being, it is structured becoming. This is one reason the union of space and time becomes so unavoidable once you stop thinking in snapshots. A snapshot can trick you. It can make the world look like pure space for a moment. But the moment you ask how one snapshot relates to another, time enters. And time does not enter as an extra label attached afterward. It enters as part of what makes the snapshots meaningful in the first place. Physics had to learn this the hard way. It began with arrangements and motions described separately, then gradually discovered that motion changes the measurement of distance and duration together, that gravity shapes clocks and paths together, that light ties causality to geometry, and that the deepest available description is not space plus time added side by side, but spacetime. That word matters here more than ever, not because it sounds modern or impressive, but because it names the level at which physical existence becomes coherent. In spacetime, an event is fundamental. Not a place alone, not a time alone, an event, a definite occurrence. This particle decays here at this moment, that star collapses there at that stage in cosmic history. You take a breath in this room now. Events are the true units of physical reality in a relativistic universe, and events are inherently space-time facts. To exist physically is to participate in a network of events linked by distance, duration, and causality. It is also worth noticing how deeply this shapes our understanding of measurement. A ruler by itself is not enough. A clock by itself is not enough. Much of physics consists in relating the two. Speed relates distance to duration. Acceleration relates changing speed to time. Energy transfer happens through processes unfolding in time across space. Fields vary from place to place and evolve through time. Even the most precise observations depend on signals travelling from one region to another during measurable intervals. If space and time were truly separable, one might hope to build a full account of the world using them independently. In practice, every serious physical description ties them together, and then there is light, still quietly doing more than almost anything else to reveal the universe's structure. Light does not only illuminate objects, it connects events, it carries information across space and time, it defines the limit of causal influence, it tells us what can affect what and how quickly any such effect can travel. That role makes light central to the very architecture of physical existence. Once light speed is constant for all observers, the old independent notions of space and time are finished. What survives is the space-time interval, and the causal order built around it. In other words, the possibility of connection itself depends on both space and time being part of one structure. Human experience also becomes more intelligible through this union. We remember the past because records were formed by physical processes in our brains and bodies. We anticipate the future because we inhabit a world in which states lead to later states. We live among objects arranged around us in space, while our own lives unfold in time. We navigate not just landscapes but schedules. We recognize friends not only by shape and face, but by continuity across years. A home is a place, yes, but it is also a history. A city is buildings in space, but also centuries in time. A life is a body and a location, but also a sequence of experiences. Our most personal realities are saturated with this partnership. That does not mean human feeling is the proof of the theory. Physics does not rest on emotion. But it does mean that once physics reveals the union of space and time, that union resonates all the way up through ordinary life. It explains why existence feels like both being somewhere and being on the way from one thing to another. It explains why the world presents itself not as a pile of positions or a bare stream of moments, but as a structured flow of events. There is also a philosophical temptation at this point to ask which of the two is more fundamental. Perhaps time is the real engine and space is secondary. Perhaps space is primary and time is merely a measure of change. People have argued these questions for centuries, but modern physics keeps pushing us away from choosing one at the expense of the other. In relativity, neither keeps its old independent status. In quantum gravity, even if space-time itself turns out to emerge from something deeper, it is still very hard to imagine physical reality giving us a meaningful where without something like a when, or a meaningful when without something like a where. The deeper the theory goes, the less helpful the old competition becomes. A useful comparison might be a sentence. You can ask whether the words matter more or the order matters more, but the sentence needs both. A pile of words with no order is not a sentence. An order with no words is not a sentence either. Meaning arises through their relation. Physical existence seems to work in much the same way. Space provides arrangement. Time provides order. Space-time provides meaningful physical structure. Remove one and the other no longer does the job alone. The universe itself, on every scale we can study, seems to agree. Galaxies exist as spatial structures that evolve over time. Stars exist as extended bodies with lifetimes. Black holes define regions of space-time whose geometry shapes both distance and duration. The cosmic microwave background reaches us from a distant time across enormous space, stretched by expansion along the way. Gravitational waves cross the universe carrying information about violent events. Even at the level of subatomic particles, existence is described through interactions occurring at space-time events. Again and again, the world refuses to let us isolate one half from the other. Perhaps the clearest sign of all is that every successful deep theory we have binds them more tightly, not less. Newton treated them separately and achieved something magnificent, but the deeper theory replaced separation with unity. Einstein did not merely discover a connection between two otherwise independent things. He showed that the old independence was the approximation. The union was the truth beneath it. Gravity then deepened the lesson by making the union dynamic. Cosmology extended it across the whole universe. Black holes stressed it to the edge. Quantum theory has not undone it. It has only made the question of that union more profound. So why does existence need both space and time? Because physical reality is not made only of things. It is made of events, relations, processes, histories, and structures. Because nothing can happen without time, and nothing physical can be arranged without space. Because causality needs order and propagation. Because identity needs form and continuity. Because motion needs distance and duration. Because light ties the whole architecture together. Because the universe, as far as every reliable clue suggests, is not built from where and when as separate ingredients tossed together in a bowl, but from their inseparable partnership. And perhaps there is a gentler way to say the same thing. Space gives the world room to be many things. Time gives it room to change. Space allows the universe to have form. Time allows it to have story. We need both for stars and atoms, but also for homes and memories, roads and seasons, births and endings, mornings and the long, patient movement of history. Existence, at least the kind we know, is not just being placed. It is being placed in motion. Not just occupying, becoming. So here we are at the end of this quiet journey, a little farther along in time than when we began, and still exactly somewhere in space, wherever you happen to be listening from tonight. We started with a question that sounded almost philosophical, and found that physics answered it with remarkable firmness. Space and time do not merely cooperate, they define each other. The universe does not hand us one and then the other. It gives us a world of events, of space-time, of structure unfolding. And if there is something comforting in that, I think it is this. The world is stranger than common sense first suggests, but it is not stranger without reason. Again and again, the same lesson returned in different forms: light, motion, gravity, black holes, cosmic expansion, quantum puzzles. All of them pointed toward one shared truth. Reality holds together because its pieces are not as separate as they once seemed. So wherever you are tonight, and whatever time your own little clock is whispering now, I hope this left you with a calmer sense of the vast thing you are part of. If you found this soothing or worthwhile, do consider liking the video and subscribing. It helps this quiet corner of thought reach other wandering minds at the end of the day. And for now, as the universe continues doing what it has always done, giving shape and sequence to everything within it, I hope the rest of your evening unfolds gently, one moment, one place, one small piece of space-time at a time.